Imagine a metal that looks like a liquid, moves on its own, and for centuries was thought to be the key to immortality. What if this very substance drove scientists insane, killed entire cities, and still hides underground today, waiting for human error? Every year, the world produces and isolates thousands of tons of this stuff. But the real danger isn't in the numbers. It's that mercury never disappears. It migrates, it accumulates, it comes back. From alchemists who breathed in its vapors to tragedies born from normal water and fish, this is the story of a metal humanity called poison way too late. Stick around till the end, and you'll learn why even today, mercury isn't seen as a resource. It's a threat you can't just bury. In ancient civilizations, people knew about mercury long before they understood how dangerous it was. They found it in nature as cinnabar, a bright red mineral that released mercury when heated. Chinese alchemists thought it was an ingredient for immortality. Egyptians used it in rituals. Romans put it in mirrors and cosmetics. Spoiler, none of this ended well. But back then, nobody was reading safety labels. In medieval times, mercury became the star of alchemy. It symbolized change and transformation because it could be both metal and liquid at the same time. Alchemists believed it was the key to making gold. They breathed its vapors, touched it with bare hands, mixed it with other substances, and genuinely wondered why their hands were shaking, their memory was failing, and weird psychological symptoms were kicking in. That's how the mad scientist trope was born. No memes required, just real consequences. The modern era brought mercury an even bigger upgrade. It was used in thermometers, barometers, manometers, fluorescent lamps, batteries, switches, and even medicine. Yep, doctors once prescribed mercury as medication, for infections, even for bad moods. The biggest fail? Treating syphilis with mercury ointments. The disease might not go away, but poisoning was guaranteed. Who remembers mercury thermometers? Drop a comment if you've got one. It was in the 20th century that humanity started to collectively realize mercury wasn't just weird, it was genuinely dangerous. It's toxic in any form, but especially sneaky because it evaporates easily and builds up in your body. Nervous system damage, coordination problems, memory loss, vision issues. This isn't some thriller script, it's what chronic mercury exposure actually does. The phrase "mad as a hatter" didn't come out of nowhere. Hat makers used mercury compounds, and craftsmen literally lost their minds. Then there's the dark chapter of ecology. Mercury doesn't disappear, it migrates. When it hits water, it transforms into methylmercury and enters the food chain. Fish eaten by humans, and suddenly the toxin's inside you. The tragedy of the Japanese city of Minamata became the symbol of this problem. Mass poisoning affecting thousands of people proved that a little mercury is a myth. In the mid-20th century, in the Japanese coastal city of Minamata, a chemical plant spent years dumping wastewater loaded with mercury compounds into the bay. The water looked normal. Fish were biting. Life went on, until people started getting mysteriously sick. First came the seizures, tremors, loss of coordination, speech problems. Then, paralysis, blindness, death. Mercury hit children especially hard. Infants were born with severe nervous system damage, even though their mothers often showed no obvious symptoms. The culprit was methylmercury, accumulating in fish and shellfish, the foundation of the local diet. The toxin didn't disappear or dilute. It intensified at every level of the food chain. For decades, the company and authorities denied responsibility, while victims fought not just disease, but indifference. Minamata showed the world a simple, brutal truth. Even minimal doses of mercury can have catastrophic consequences when they become part of the environment. It was the end of the illusion of safe mercury. Mercury deposits exist today, but attitudes toward them are radically different from centuries past. The primary natural source of mercury remains cinnabar, a bright red mineral, mercury sulfide, which forms in hydrothermal deposits, often near volcanic zones, and fractures in the Earth's crust. It's from cinnabar that metallic mercury was historically obtained through roasting, and this process has remained virtually unchanged technologically. What changed were the scale and the regulations. The largest known mercury deposits in the 20th century were developed in Spain, Italy, China, Kyrgyzstan, Mexico, and Algeria. Spain's Almaden deposit was once considered the world's largest, and for centuries supplied a significant portion of global production. Today, it's basically mothballed, like most classic mercury mines. The reason's simple: demand tanked, and the environmental and health risks became too obvious to ignore. China remains the main mercury producer now, but even there, extraction volumes are way lower than in the past. Many countries aren't opening new deposits. They're working with existing stockpiles or secondary mercury recovered from industrial waste recycling and dismantling old equipment. The world has essentially shifted from active mining to a mode of control and reduction. Modern mercury deposits are increasingly viewed not as a future resource, but as a problem that needs to be safely isolated. Some deposits get shut down, others are reclassified as geological landmarks or monitoring sites. Mercury still sits deep within the planet's core, but its story as a strategic metal is nearly over. Now it's an element humanity handles with extreme caution. Underground mercury ore extraction in China typically starts with a narrow portal carved into rock, the entrance to a mine shaft. It might look like a dark rectangle in stone, reinforced with concrete or metal frames. Inside, a tunnel several yards wide, where small mining vehicles can pass through or conveyor belts can run. The working space is cramped and low. The ceiling's propped up with beams, the walls damp, streaked with reddish or dark brown veins of cinnabar. Lighting: cold fluorescent lamps casting harsh shadows. The air's heavy, so ventilation is critical. Along the tunnels run air ducts, humming and pushing fresh air deep into the mine, while simultaneously pulling out dust and gases. The ore itself is extracted using drill and blast or mechanical methods. First, drilling rigs bore a series of holes into the rock. It looks like rhythmic metal biting into stone. Then, if blasting is used, minimal charges are placed in these holes. The explosions are controlled, small. The goal isn't to destroy everything, but to peel away the rock. After that, the tunnel fills with dust that settles for minutes, while ventilation runs at full blast. Next, mechanization takes over. Front-end loaders rake up the broken rock, or gather it in buckets and dump it into mine cars or onto a belt conveyor. The stone looks uneven, with flecks of red. That's cinnabar, the main target. People try not to touch the ore with bare hands unless they have to. The dust is dangerous, so workers wear respirators, thick coveralls, gloves. How strictly this is enforced depends heavily on the specific operation. If it's a semi-underground or open-pit mine, the picture is different. There you'll see step-like benches cut into the rock where equipment moves around. Excavators strip away layers of ore, trucks haul it up to the surface. But even here they try to avoid huge open spaces, mercury dust and fumes, enemy number one, which is why open pits are less desirable for this kind of metal. All that ore doesn't sit around in the mine for long. It's immediately transported to the surface in sealed containers or on covered conveyors to minimize dust dispersal. At the mine exit, you'll often see washing stations, equipment, and sometimes the workers themselves get hosed down so they don't carry cinnabar particles beyond the production zone. After extraction, the ore is crushed and sent for heat treatment. Cinnabar is heated in specialized furnaces, where the mercury sulfide breaks down and the metal evaporates. This stage is the most dangerous. Mercury vapors are toxic, so modern facilities are equipped with sealing, condensation, and filtration systems. The vapors are cooled, after which the mercury transitions to a liquid state and is collected in sealed containers. Formally, all these processes are supposed to occur in a closed loop with no emissions into the environment. In practice, this is where the biggest questions arise. At large state-run or licensed operations, oversight is stricter. There's air monitoring, waste disposal protocols, and tracking of every kilogram of metal. At smaller or semi-legal operations, the risks are significantly higher, and these have historically been the source of local contamination and poisoning. What if I told you there's a metal that can't be destroyed by fire, pressure, or time? A material without which aviation would stop, lights would go dark, and space engines would fall silent. And yet, it's so rare that the entire world fights over every single gram. But here's the real kicker. By the end of this video, you'll learn a secret about tungsten that the industry hides and almost nobody talks about. Something that'll flip your understanding of the metal holding civilization together. Tungsten is a true engineering phenomenon. Its unique properties let us push the boundaries of what's possible in technology, from deep underground to the heights of space. Its story, a story of endurance and unmatched strength. Tungsten is element 74 on the periodic table, one of the transition metals. It has the highest melting point of any metal on Earth, a staggering 6,192 degrees Fahrenheit. To put that in perspective, that's a temperature where most other metals would have vaporized long ago. On top of that, tungsten has the highest tensile strength of any pure metal, at temperatures above 3,000 degrees Fahrenheit. It's incredibly hard and dense, making it irreplaceable for applications demanding maximum resistance to wear, deformation, and extreme temperatures. Tungsten doesn't occur in pure form. It's extracted from ores, with the most common being wolframite and scheelite. Wolframite is a complex compound of iron, manganese, and tungsten, while scheelite is calcium tungstate. These ores, hidden deep in the Earth's crust, are the raw material for all subsequent industrial processing. The world's major tungsten producers include countries like Vietnam, China, Russia, and Canada, which hold significant reserves of this strategic metal. The tungsten extraction process is a complex sequence of mining and metallurgical operations. It starts with exploration and ore extraction from underground mines or open-pit quarries. Geologists use various methods to identify and assess tungsten ore deposits. Then, using powerful drilling rigs and explosives, the ore is extracted from deep within the Earth. It's tough, dangerous work that demands cutting-edge technology and strict safety standards. Thousands of tons of ore are hauled to the surface every single day. After extraction, the ore heads to a processing plant. Here it goes through several stages to separate valuable wolframite or scheelite from other rock. First, the ore gets crushed in crushers and mills until it's a fine powder. Then various enrichment methods kick in: gravity separation, magnetic separation, and flotation. These processes yield a concentrate containing 60 to 70% tungsten trioxide, which is an intermediate form. The concentrate is then processed at metallurgical plants to extract pure tungsten. It's a complex chemical process that can involve alkaline leaching, precipitation of ammonium paratungstate, and its subsequent roasting to produce tungsten oxide. The tungsten oxide is then reduced to metallic tungsten by heating it in a hydrogen atmosphere at temperatures ranging from 2,000 to 3,300 degrees Fahrenheit. The result is a fine tungsten powder, which forms the foundation for all subsequent products. From this powder, through sintering, tungsten rods, bars, and other blanks are formed. Tungsten powder is pressed under high pressure into the desired shape, then sintered at extremely high temperatures in a hydrogen atmosphere. This allows the powder particles to bond together, creating a dense, strong material. One of the most critical applications: manufacturing tungsten carbide. Some seriously tough stuff. These alloys combine tungsten with carbon, plus cobalt or nickel as a binder, creating one of the hardest man-made materials on Earth. They're used to make cutting tools, drill bits, end mills, lathe inserts that can slice through the hardest metals and alloys. Without tungsten carbides, modern manufacturing, metalworking, and oil and gas extraction would grind to a halt. A single pound of tungsten can become a drill bit capable of boring through thousands of feet of rock. Talk about efficiency. Tungsten also sees heavy use in military applications for armor-piercing rounds and bullet cores. Thanks to its extreme density and hardness, Tungsten alloys have exceptional penetration characteristics, delivering devastating effectiveness against armor. It's also used in heavy armor plating and counterweights. In electronics and electrical engineering, tungsten is indispensable. It's used to make filaments in incandescent bulbs, welding electrodes, electrical contacts, and other components that need high heat resistance and electrical conductivity. Because of its sky-high melting point, it's used in the aerospace industry for parts exposed to extreme temperatures. High-temperature tungsten alloys are used in jet engines, turbines, and other devices operating under extreme heat. Alloying with tungsten boosts the heat resistance of other metals. In medicine, tungsten is used in manufacturing X-ray tubes thanks to its high atomic number, which effectively blocks X-rays. It's also used in radiation shielding, similar to lead, but with way less toxicity. On top of that, tungsten's used to make ballasts and counterweights in race cars, aircraft, and yachts thanks to its crazy high density. It's even a component in some jewelry because of how hard it is and how resistant to scratches. Tungsten is one of the rarest elements in Earth's crust, which makes mining and producing it especially valuable. Global tungsten reserves that are economically viable to mine are estimated at roughly 3 to 3.5 million tons. However, when you factor in potential resources that haven't been explored yet, the total volume could be significantly higher. That's obviously way less than reserves of metals like iron or aluminum, which really highlights its strategic value. Global tungsten production each year, measured in tons of pure metal, or tungsten oxide equivalent, fluctuates, but in recent years, it's been somewhere between 85,000 and 100,000 metric tons annually. This figure includes both primary extraction from ores and recycling, which is becoming increasingly important. Imagine this. You could take a worn-out tool that's already served its purpose and transform it back into something brand new, without spending the energy and resources to mine ore from scratch. That's exactly what happens with tungsten. Tungsten recycling is one of the most advanced and efficient processes among all metals. By various estimates, up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number. It shows just how valuable this metal is and how much economic sense it makes. Where does used tungsten come from? The main source of secondary raw material for tungsten is, of course, worn-out carbide tools. Those same cutting tools, drill bits, milling cutters made from tungsten carbide. After heavy use, they wear down, lose their edge, or break. Instead of tossing them in the trash, they're collected and sent to recycling plants. Other sources include scrap metal containing tungsten, leftover waste from tungsten product manufacturing, plus some electrical contacts and wires. Recycled tungsten is significantly cheaper to produce than primary metal because it eliminates the expensive and energy-intensive stages of mining ore and initial processing. Recycling dramatically reduces the environmental footprint of tungsten production. It minimizes the need for mining operations, cuts energy consumption, reduces industrial waste, and lowers greenhouse gas emissions. This makes production more green and responsible. Every year, the world mines over 900,000 tons of rare earth metals. Without them, not a single smartphone, electric car, or wind turbine would work. But there's one place where most of them are born. Baiyun Obo, a massive quarry in the heart of China that supplies 70% of all the rare metals on the planet. Here, the earth glitters with metallic dust, and every dump truck hauls raw material for the future. But behind this shine hides a dark truth. Lakes of toxic waste, and the price nature pays for technological progress. Stick around till the end, and you'll discover how dust and poison create the foundation of modern civilization. The story of Baiyun Obo started back in the 1920s, when geologists discovered a strange ore in this area, a mix of iron and minerals unknown at the time. In the 1950s, Chinese scientists realized that hidden here was a treasure trove of rare metals: neodymium, praseodymium, cerium, yttrium, and lanthanum. Since then, Baiyun Obo has become the heart of China's strategy, that would eventually turn the country into the undisputed leader of the global rare earth market. Every year, about 270,000 tons of rare earth concentrate are mined here, more than all other countries combined. It all starts simply. Massive dump trucks the height of a 2-story building pull up to the edge of the quarry, where giant excavators with buckets like a dinosaur's mouth rip out chunks of monzonite ore. Each bucket can hold over 100 tons. The dust rises in columns, and it feels like the very air here is saturated with metal. But extracting the ore is just the beginning. The real value is hidden in microscopic inclusions of rare earth minerals. Their share in the rock is only a few %, so after extraction, the ore is crushed and sent to processing plants, where a complex chemical story begins. First, the ore is ground to dust, then subjected to flotation, a process where particles suspended in water are separated using reagents. Rare earth particles stick to air bubbles, rise to the top, while the rest settles to the bottom. This is just the first step, because the concentrate still contains plenty of impurities: iron, calcium, fluorine. Next comes chemical extraction, which transforms the concentrate into high-purity oxides. This is an extremely complex process. In specialized reactors, the ore is treated with acids, usually sulfuric or hydrochloric, sometimes with the addition of fluoride compounds. After this, the resulting solution is separated into fractions using organic solvents. Each element, neodymium, praseodymium, cerium, has its own chemical quirks, so the process requires dozens of sequential cycles of extraction, precipitation, filtration, and drying. It's these oxides that then go into the production of permanent magnets, the main consumer of rare earth metals. For example, one iPhone might contain less than 1/10,000th of an ounce of neodymium in the speakers and vibration motor. In a modern wind turbine, nearly 1,400 pounds of this element. And here's the wow fact. Just 1 gram of neodymium can provide a magnet for a turbine that generates electricity for roughly 1,000 homes. It sounds like an energy miracle, but it has a flip side. The problem is that chemical processing of rare earth ores is extremely toxic. Every gram of pure metal means tons of waste. In the Baotou area, near Bayunobo, real waste lakes have formed. Black, acidic bodies of water where radioactive elements, fluorides, and heavy metals accumulate. They're visible even from satellite. Even with modern cleaning technologies, chemical processes leave their mark on the environment. Local residents tell stories that, over the past decades, dust from the quarry and processing plants has changed the soil color, and grass around the area has been growing worse. However, the Chinese government is taking measures, implementing closed-loop water systems, controlling acidic runoff, and converting some facilities to new, green technologies, where instead of traditional acids, they use ionic solutions and membrane separation. All this is being done not just for environmental reasons, but also because China aims to maintain its dominance in the global rare earth metals market. Today, it accounts for 70% of global production and over 90% of finished oxide and magnet production. Other countries, the US, Australia, Vietnam, Malaysia, are trying to develop their own deposits, but they haven't come close to Chinese scales yet. Bayunobo has become more than just a quarry. It's a symbol of the technological era, where Earth transforms into smartphones and ore becomes electric wind. Right here, among mountains of metallic dust, the elements that power digital civilization are born. There's a certain irony in this. In the quest to create a green future, humanity has become dependent on one of the dirtiest industries. Magnets for electric cars and turbines, batteries, solar panels. All of this requires metals extracted from places like Bayunobo, and the greater the demand for clean energy grows, the deeper this giant wound in the earth becomes. Despite this, for China, Bayunobo is a source of national pride. Thousands of people work here, and the territory itself is equipped with modern infrastructure, conveyor systems, automated drilling rigs, chemical plants that operate almost without human involvement. On the surface, sensors are installed that track air composition, and in reservoirs, pollution levels are monitored in real time. Every dump truck descending into the quarry is part of a giant machine that supplies the world with energy, data, and sound. And when we hold a lightweight smartphone in our hands, it's worth remembering that a piece of this device, maybe even that very magnet in the speaker, was once dust in the Mongolian desert. Neodymium is one of the most famous, and at the same time, most mysterious rare earth metals. It's a silvery white, shiny, fairly soft metal that easily oxidizes in air, so it's usually stored under a layer of oil, or in an inert atmosphere. Sounds unremarkable, but this element has become the quiet engine of the modern technological revolution. Without neodymium, wind turbines, electric cars, headphones, laptops, and even rockets wouldn't work. In pure form, neodymium doesn't have the magnetic properties it's valued for. They appear when it's combined with iron and boron, forming an alloy. This is the material used to make the most powerful permanent magnets on Earth. One neodymium magnet can hold weight hundreds of times its own. In industry, it's called a supermagnet, and for good reason. It's what makes compact electric motors, miniature speakers, and highly efficient generators possible. One study indicates that between 2001 and 2021, Bayun Obo supplied about 60% of neodymium from China's total neodymium extraction. On one hand, Bayun Obo is a remote, harsh, and dusty place. On the other, it evokes an almost magnetic curiosity in those who want to see what modern civilization looks like in its raw material form. Bayun Obo today is not just a mine, but an entire complex with its own small town, a rare earth elements museum, and even a special viewing platform from which you can see the giant pit going hundreds of feet deep. The flow of tourists here is small by Chinese standards, but steady. These are mainly engineers, geology students, bloggers, eco-tourists, and those fascinated by industrial landscapes. In 2019, local authorities even declared Bayun Obo part of the Industrial Heritage of Inner Mongolia route to show how mining and processing have transformed the region. In tourist brochures, this place is called the heart of the rare earth planet. The road to the quarry leads through endless plains and low hills, where the wind almost never stops. The air carries the smell of metal, and from a distance, the quarry looks like a giant amphitheater, where Earth plays the starring role. Tourists aren't allowed close to the mining zone. It's too dangerous, but there are several safe spots from which you can take photos. The most striking moment is when quarry dump trucks slowly move at the bottom of the pit. They look like toys. The scale is so massive. So, I know North Carolina doesn't sound particularly exotic, but what's being made here flies at 66,000 feet above the Pacific Ocean and keeps 400 passengers in the air at the same time. This is the factory that produces blades for the GE9X turbine engine series, the largest commercial jet engines in the world today. One of these engines weighs about 9 tons, generates thrust up to 105,000 pounds. Sorry, that's roughly 460 kilonewtons, and costs around $50 million. But we're not here because of the engine. We're here because of one specific part that's about the size of your palm and costs more than a nice car. A turbine blade. In the hot section of the engine, in what's called the high-pressure turbine, there are between 160 and 180 of them per wheel, depending on the stage. Each one weighs roughly 10.5 to 14 ounces. But the conditions it operates in, this isn't engineering anymore. It's straight-up torture for common sense. The temperature of the gases flowing around the blade during engine operation, 2,700 to 2,900 degrees Fahrenheit. That's higher than the melting point of steel, higher than the melting point of the very material the blade is made from. How it doesn't just melt, I'll tell you in a minute, because it's one of the coolest things I saw at this facility. The blade material is a nickel-based superalloy. The exact recipe is classified, and they didn't tell me the full breakdown, which is fair. But the general principle is known. Each element is responsible for something specific. Take rhenium, for instance. It provides heat resistance and slows down creep. That's when metal under prolonged stress and temperature deforms completely. The raw material cost for a single blade runs from 200 to 300 euros just for the metal, before anyone's even touched it. Now, how it all begins. The blade manufacturing process is investment casting, also known in the industry as lost wax casting. First step, the wax model. An exact replica of the future blade, including all internal channels, is created from wax under pressure in a metal mold. The precision of this mold, plus or minus 20 micrometers. That's about a quarter of the thickness of a human hair. If the mold deviates any more than that, it goes back for refinement. But the wax model is just the outer form. Inside the blade, there are also cooling channels, thin, winding tunnels through which cold air from the compressor gets pumped during engine operation. That's why the blade doesn't melt, even though the surrounding gas is hotter than its own melting point. Inside, air at temperatures of 500 to 600 degrees are formed separately, using ceramic cores that get inserted into the wax model before casting. The core looks like a thin, sturdy comb, and it occupies exactly the space where the channel will eventually be. The wall thickness between the blade's outer contour and the internal channel ranges from 1 to 2 millimeters. Any thinner, and the blade becomes brittle. Any thicker, and the cooling can't keep up. Next, the wax model gets dipped into a liquid ceramic slurry and coated with fine ceramic sand. Dip, pull out, dry, and repeat the cycle 8 to 12 times. Each layer dries for 4 to 8 hours. After the final layer, you get a ceramic blob about 10 millimeters thick, hard, rough to the touch, kind of like papier-mâché if papier-mâché were made from space shuttle material. Then this whole thing, with the wax still inside, goes into an autoclave, where at temperatures around 300 degrees Fahrenheit and elevated pressure, the wax melts out through a small opening. Hence the name, lost wax casting. What's left inside is a perfect negative of the blade shape. The ceramic holds its form, the cores stay in place. Now comes the metal pour. This is the part I came for. The molten metal gets heated to around 2500 to 2700 degrees Fahrenheit and poured into the ceramic mold. But they don't just pour it and wait for it to solidify. The mold gets slowly withdrawn from the heating chamber at a rate of about 1/10 to 1/5 of an inch per minute. That withdrawal speed controls how the metal crystallizes. If everything's done right, the entire blade, from root to tip, becomes a single crystal. Not a single grain boundary throughout the entire volume of metal. That's single crystal casting. Grain boundaries, the weakest spot in any metal. That's where cracks start under prolonged stress and heat. If there's only one grain, there's no boundary, no failure points. Heat resistance jumps roughly 30% compared to ordinary polycrystalline casting. After cooling, they break the ceramic shell, just mechanically, with hammers and vibration. Out comes a gray blade with ceramic cores inside. The cores come out in an alkaline solution at roughly 210 degrees. The chemistry dissolves ceramic, but leaves the metal untouched. This takes 4 to 8 hours. After washing, those same cooling channels remain in the center, clean, precise, completely open. Then they check the blade. X-rays reveal pores and cracks inside the metal. Fluorescent liquid catches surface defects. A special probe passes through each cooling channel, verifying it's not blocked by ceramic residue. If even one cooling channel is partially blocked, the blade goes straight to scrap. Not to rework, straight to scrap. Because you can't fix that. The rejection rate at this stage runs 2 to 5% per batch. Doesn't sound like much, but given what each part costs, we're talking real money. After inspection, heat treatment. The blade goes through multiple temperature cycles. First, around 1900 degrees for several hours, then a gradual cool down. This process evens out the internal stresses that formed during casting and locks in the alloy's microstructure. The exact heat treatment protocol? Also classified. When I asked, the manager who was walking me through just smiled and changed the subject. Final stage, protective coatings. First comes a metallic bond coat, nickel and aluminum based, applied using a plasma spray process. That's the foundation. On top of that goes the thermal barrier coating, zirconia stabilized with yttrium. It's ceramic, and it's that ceramic layer that absorbs the first several hundred degrees from the screaming hot gas stream. This layer is between 100 and 2 micrometers thick. The application looks like spray painting in a chamber. The blade rotates, the plasma gun moves along it, following a preset path. But the temperature of the plasma stream during application is around 18,000 degrees Fahrenheit. For comparison, the surface of the sun is about 10,000 degrees. So the tool is nearly twice as hot as a star, but the blade itself doesn't heat up more than 4 degrees, because the entire process is incredibly fast and incredibly precisely controlled. The finished blade goes for final weighing, measurement, and registration. Each one gets an individual serial number and a passport where all parameters are recorded, from the chemical composition of the melt to the results of every control measurement. This document is kept for as long as the engine lives, and that's 20 to 30 years and tens of thousands of flight hours. On my way out, I asked how many blades they made per month. They told me it was in the range of several thousand units across all sizes. They wouldn't give me an exact number. But when you consider that one engine needs several hundred hot section blades alone, and orders for the 9X remain backed up for years ahead, you can imagine the scale. You're the best. Subscribe so you don't miss the next facility. It's going to be even more interesting. Write in the comments where you're from, and maybe next time I'll visit your city. Houston, Texas, high noon. The sun here doesn't just shine. It presses down on your shoulders like a heavy, hot blanket. The air above the scorching asphalt shimmers with heat waves, and your lungs fill with a thick, distinct smell. A mix of heated rubber, dry prairie, and diesel fuel. I'm standing at the gates of the Jinan plant, the world's largest tire recycling facility, and I can feel the soles of my boots starting to soften on the blistering Texas ground. Today, I'm not just a tourist. I'm a witness to a massive technological alchemical process, where what the world considers waste that won't decompose gets transformed into energy, and the very foundation of the highways we drive on. Houston didn't just greet me with sunshine, it slammed me with a wall of sticky heat that folks down here in Texas call the devil's breath. But the second I stepped through the entrance to Jinan's facility, the sounds of the city, distant highway hum and rustling wind, instantly shifted into something far harsher. Industrial chaos. But chaos that's perfectly ordered, rhythmic, almost primal. The first thing that hits you isn't the sound, it's the vibration. You don't just hear it. It rattles your chest like a low bass line at a rock concert. That's the giant motors firing up the heart of the plant. And spread out before me are the real black Himalayas. Thousands, maybe tens of thousands of used tires stacked into neat but staggering mountains. Everything's here. Thin wheels from compacts that only ever touched smooth asphalt, all the way up to massive donuts from mining dump trucks, treads tall as a person. They all came here to die, so they could be born again. The smell here is something else. It's not just the stench of rubber. It's a complex cocktail of heated polymer, traces of road tar baked into the treads, and hot metal. The Texas sun mercilessly scorches these black surfaces, and the heat radiating off them makes you feel like you're standing next to an open oven. The air between the mountains has solidified. It's thick and oily. I watch as another truck rolls up. The hydraulics groan as the bed lifts, and hundreds of tires tumble down with a muffled rumble. Thump, 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 cascading to the foot of the black mountain. This sound of rubber hitting rubber layers over that same endless vibration from the plant's engines. It creates this uncanny sensation of being inside a living organism. The plant breathes with this rhythm. It's hungry, and these mountains are its food. The vibration intensifies when the feed conveyors kick on. You see these massive manipulators, like the claws of prehistoric monsters, tearing into the piles, snatching their prey. In this place, on the edge between old junk and raw material, you feel tiny. We're following the conveyor belt that leads straight into the heart of the main floor. Here, that vibration I mentioned earlier transforms into physical force, pounding against your eardrums. We approach it, the primary shredder. If those mountains of tires were a graveyard, then this machine is the industrial meat grinder that knows no mercy. The first thing that hits you is the contrast between speed and power. You'd expect the shredder to spin at breakneck speed, flinging chunks of rubber in every direction like a blender. But no, the shredder's shafts move slowly, almost lazily. But within that slowness lies colossal torque, force capable of crushing stone. It's a deliberately engineered method. Low rotational speed prevents the rubber from overheating, keeping it from melting and sticking to the blades, which would turn the machine into a gummy trap. When the next tire, say, a massive wheel from a Texas pickup, hits the rollers, something happens that makes you flinch. The tire tries to hold its shape. Its steel belt, that same skeleton that carried tons of weight on the road, puts up one last fight. But hardened blades made from special alloy dig into the tread like the teeth of a prehistoric predator. 1 second, and you hear that distinctive crunch as the steel wires inside the rubber snap under hundreds of tons of pressure. In that moment, bright, angry showers of sparks fly out of the shredder's jaws. It's the friction of the steel belt against the blades, creating miniature lightning bolts inside the machine's dark belly. The heat here becomes almost unbearable. If it was just hot outside in Houston, near the shredder, the air heats up to a temperature where the sweat on your forehead instantly turns sticky with rubber dust. You can smell the frictional heat, sharp, metallic, with notes of burnt sulfur. It's the smell of matter being physically destroyed. Dust is everywhere here. It's not just floating in the air, it's dancing in the beams of industrial lights, settling on every surface like black velvet. These are tiny rubber particles released during the tearing process. You can see chunks falling from beneath the rollers onto the exit conveyor. This isn't a tire anymore. These are shapeless, torn scraps of rubber, roughly the size of an adult man's palm. Mangled strands of steel wire stick out from them, those same cord fangs that magnets will pull out in the next stage. The chunks of shredded rubber that just passed through the shredder's jaws move along on the conveyor belt. They look terrible, torn, dirty, hot, with those same mangled steel wire threads, cord fangs, sticking out from every black edge. Right now, one of the most cinematic stages at the Jinan plant begins. We're approaching above the conveyor, where chunks of tires race by in an endless stream, massive blocks hang suspended. Overhead electromagnetic separators. They hang low, almost touching the black flow, humming with voltage. What happens on the belt resembles an uprising of the dead. When a ragged chunk of rubber enters the magnet's zone, the steel threads inside it react instantly. You see it with your own eyes. Metal wire that a second ago was part of a solid framework suddenly comes alive. With savage force, it tears free from its rubber prison, dragging the entire chunk with it, or simply slipping out like a knife through butter. Metal literally shoots upward, defying gravity. It looks like strange, aggressive magic. Thousands of steel needles and twisted wires slam into the magnetic belt with a loud crash, spinning perpendicular to the main conveyor. This is that endless clacking, the sound of thousands of metal fragments hammering into the separator's steel armor. The heat in this zone is unique. The magnets consume a massive amount of electricity and generate heat themselves, mixing with the warmth from freshly cut rubber. You're standing in a cloud of a specific smell, a blend of ozone, which always accompanies powerful electromagnets, and warm, raw metal. It's the smell of a forge, but without fire. Look to the left of the main conveyor. Another mountain is growing there. a mountain of pure steel. The magnetic belt carries the captured metal beyond the rubber stream, and, where the magnetic field vanishes, dumps it into a separate hopper. You're looking at springs coiled into spirals, long sharp needles, tiny metal chips. Everything gleams under the factory lights with a cold, bluish glow, contrasting sharply against the matte black of the rubber. Stripped of its steel skeleton, the rubber moves forward into the darkest and most airtight section of the plant. Now that the metal's gone, the rubber chunks look surprisingly light, but that's just an illusion before the final battle. We're entering the secondary granulation zone. High-speed granulators transform the torn pieces into perfect rubber crumb. The air here is thick with black snow, fine dust swirling through beams of light. Each granule passes through a system of vibrating screens, where they're sorted by size down to a fraction of an inch. But the real climax lies ahead, inside the sealed steel pyrolysis reactors. We approach the long, insulation-wrapped cylinders. This is the zone of quiet energy. There's no open flame here, but inside, hellish heat reigns, 850 degrees Fahrenheit. The key secret? Total absence of oxygen. The rubber single second, over 100 tons of new trash gets created around the world. Think about it. While you're watching this video, an entire truckload of waste appears on our planet. Where does it all end up? For years, the answer was simple: China. That's where Europe, America, and Japan shipped millions of tons of used bottles, paper, and scrap metal. But one day, China said, "That's enough." And suddenly, the world faced a garbage meltdown. But here's the mystery. Why would a country that banned importing other people's trash start searching for it just a few years later? Stick around till the end. You'll discover the secret that flipped the global recycling industry upside down. For many, many years, the entire world, especially wealthy countries in Europe, America, and Japan, got comfortable with a very convenient setup. They'd collect their trash, old plastic, paper, scrap metal, and simply ship it off to China. Massive container ships sailed across the oceans, loaded with tons of used soda bottles, old newspapers, and broken toys. China was like the world's global trash can. But not just a can. It was also a massive recycling operation. Chinese factories would take this waste, sort it, process it, and turn it into new products that they'd sell right back around the world. It was incredibly profitable for China. They got cheap raw materials and created jobs. And for other countries, it was perfect. They got rid of their garbage problem for relatively little money. Everybody was happy, right? Well, almost. But then, around 2018, China said, "Enough." Imagine a huge meeting of Chinese officials where the decision rang out: "We're done accepting other people's trash." They called this policy, very characteristically, National Sword. It was like if your neighbor, whose garage you'd been dumping your junk in for years, suddenly said, "That's it, take it all back. My garage is full and I'm sick of this." And that's when real chaos erupted. Countries that had been carelessly shipping their waste to China for years suddenly found themselves with millions of tons of garbage with nowhere to go. Picture this. Warehouses across Europe and America started filling up with mountains of plastic and paper that were supposed to sail to China, but now had no destination. It was a genuine shock to their recycling industry. What were they supposed to do with all this trash? Dump it in the Pacific Ocean? Toss it in deserts like in post-apocalyptic movies? Massive. Some countries started burning waste in incinerators, which isn't great for the environment since it pollutes the air. Others scrambled to find new trash cans in Southeast Asia, Vietnam, Malaysia, Indonesia. But these countries quickly started pushing back too, because they didn't want to become the world's dumping grounds either. But here's where it gets really interesting. While the world frantically searched for somewhere to shove their plastic mountains, China started feeling a strange hunger. A hunger for plastic. A hunger for waste paper. A hunger for scrap metal. Seems impossible, right? A country that generates the most trash in the world suddenly experiencing a shortage of it? It's like a millionaire who suddenly went broke and is now searching for loose change under the couch cushions. The thing is, Chinese industry had gotten hooked on this imported high. Recycling plants, of which there were, to put it mildly, plenty in the Middle Kingdom, had gotten used to working with cheap, abundant, though not always quality, imported waste. Imagine a huge factory that processes tons of plastic bottles from Germany or the US every day. Its conveyor belts ran non-stop. Its workers knew their job. Its owners counted their profits. And suddenly, bam! The tap of imported raw materials got turned off. National Sword didn't just cut off imports. It left this entire massive industry without its usual food supply. Factories stood idle, capacity sat unused, and business owners pulled their hair out. But why couldn't they just switch to their own Chinese garbage? After all, there are billions of tons of it, right? That's where the devil's in the details. The problem isn't the absence of trash altogether, but the absence of quality, sorted, clean raw materials. The problem is that Chinese citizens don't know how to sort trash. Imagine this. People lived for decades, just like we used to, following the principle of everything in one bin, then off to the dump somewhere. That's the easiest way, you gotta admit. No need to think about anything. No need to separate anything. Just toss it and forget it. And this system that formed over generations, this habit that took root deeper than the oldest tree, suddenly turned out to be wrong. The Chinese government, facing these trash mountains growing faster than bamboo after rain, decided, yeah, this has to stop. We're starting to sort. But something went wrong. Sure, in big cities like Shanghai, where millions of people live in tight quarters, now you don't just throw out trash. You have to divide it into 4, sometimes 5 different categories. Wet waste, dry waste, recyclable waste, and hazardous waste. And all this has to be thrown out at strictly defined times, in strictly defined containers. But that's just the tip of the iceberg. First, even what gets sorted often doesn't meet the cleanliness standards required for recycling. Imagine a plastic bottle you tossed in the right container, but it was poorly washed and still had yogurt residue inside. Or a pizza box soaked with grease. Things like this, if there are too many of them, can ruin an entire batch of raw materials, making it unsuitable for recycling. Recycling plants that previously worked with more or less standardized imported plastic that had already gone through initial sorting abroad suddenly faced Chinese reality, a mixture that requires additional, expensive cleaning stages, or simply gets rejected. Second, logistics. Collecting billions of tons of trash is one thing, but collecting it in such a way that it reaches recycling plants as clean, sorted raw materials that can be economically viable to recycle, that's a completely different story. In many areas of China, especially in smaller cities and rural areas, the secondary raw material collection system is still very primitive. There, trash is still collected haphazardly, and sorting often happens right at the dump site, by hand, which hardly guarantees high quality. But there's another interesting angle here. China is a country that's constantly trying to upgrade itself, to become a leader in everything. And with trash recycling, it's the same story. After National Sword, they decided, okay, if we can't import, we'll build the world's best system ourselves. And they started building, modernizing, investing. New, modern, high-tech recycling plants appeared. They're equipped with the latest equipment, capable of processing massive volumes of secondary raw materials. But they need these raw materials. Clean, quality, preferably pre-sorted. And that's where the paradox emerges. There are plants, there's technology, there's the will to recycle, but there's not enough of the right trash. Picture a giant gleaming factory where robots work, but the conveyor belts move sluggishly because trucks haven't brought enough quality plastic. Or they brought it, but it's so contaminated that it has to be sent to the landfill instead of being recycled. It's like building a luxury restaurant with the best chefs, but having a shortage of fresh ingredients. This hunger for trash isn't just an economic problem, it's also a driver for further change. It's forcing China to accelerate reforms in waste management. The government is putting even more pressure on cities to improve their waste separation and sorting systems, educate the public, and implement fines for improper sorting. New logistics chains are being created for efficient collection and transportation of sorted secondary raw materials to recycling plants. Systems based on artificial intelligence and robotics are being developed for more accurate and efficient trash sorting. Imagine sorting robots analyzing every piece of plastic, determining its type and cleanliness. China aims not only to recycle, but also to use recycled materials in its own production, thereby closing the circular economy loop. This means that a system that previously relied on external sources of raw materials now has to completely reorient itself to internal, more finicky sources. And this trash hunger paradoxically pushes China to finally build a truly efficient and environmentally responsible waste management system. It's like a dragon that created a problem for itself just to heroically solve it later. And who knows, maybe in a few years, China will be not only the world's biggest trash producer, but also its biggest and most efficient recycler. That's the tangled but fascinating trash story from the Middle Kingdom. This single tank holds an entire Olympic pool's worth of fuel. Hard to believe. Look at this, 10,000 gallons in each one of these tankers. I'm standing here in a massive, towering factory right in the heart of America, where these steel giants are born from scratch. This isn't just a workshop, it's a true industrial cathedral, where instead of organ music, you hear the roar of metal, and instead of incense, you smell ozone and white-hot steel. Today, we're diving into the process of building a fuel tanker, those same shiny cigar-shaped missiles that race down highways, loaded with gasoline or diesel. I've already walked these floors, talked to workers whose faces are hardened by heat and labor, and now I'm going to tell you everything. To do that, you need to follow me. Don't fall behind. Ready? Then let's roll. This is going to be incredibly fascinating. First comes the raw material, the lifeblood of a future giant. It all starts not with ore, but with perfectly flat, thick steel sheets arriving on railroad platforms. Picture a sheet of metal 25 feet long and 10 feet wide. It's like a small billboard, only made of steel. And this steel isn't ordinary. It's a special alloyed blend containing chromium for rust resistance and molybdenum for incredible strength. It's engineered to withstand insane pressure, impacts, and Workers in bright hard hats, like ants around a giant treasure, use overhead cranes gliding smoothly beneath the ceiling to lift these sheets and carefully stack them. Everything's computer controlled, with laser scanners checking every millimeter of surface for detected defects, microcracks, or irregularities. Only perfect raw material gets the green light to move forward. Now it's time to cut the metal. Sheets roll from the warehouse onto the cutting table. A portal looms over the sheet, and a cutting head hisses along its track. This is a giant plasma cutter. From the nozzle, under massive pressure, erupts a jet of gas heated to tens of thousands of degrees Fahrenheit. It's like a tamed lightning bolt. That jet slices into the metal like butter. Sparks fly in every direction. Like fireworks, the air hums with power, and the smell of ozone fills the shop. A computer program guides the cutter along a perfectly calculated path, carving 2 or 3 panels for the future tank from a single sheet with accuracy down to a 1/4 inch. Each panel has all the necessary openings for future valves and hatches. After cutting, the panels are still hot and a bit rough around the edges. Next up, bending the panels, giving them shape. That's where the real heavyweights come in. 200-ton hydraulic presses. Picture a giant machine that slowly, but with unstoppable force, bends thick steel plate like it's a sheet of paper. A crane feeds in a flat panel, and the machine, pressing it against a massive curved die, transforms it into a perfect arc. That's how the cylindrical sections of the tank and the rounded ends are born. The cylindrical body gets assembled from several of these sections and ends up 50 feet long and 10 feet in diameter. After each bend, workers check angles and radii using special templates and tape measures. Everything has to be perfectly round. Why? Because in a circular vessel, pressure distributes evenly. Any warping, any flat spot, that's a stress point where, under fuel pressure, the tank could rupture. Fuel doesn't tolerate compromises. Welding, that's where the heart of the process is, where separate pieces become one whole. This is where real craftsmanship lives. Welders in masks with automatic ultraviolet filters aren't just handling simple equipment, they're operating automated submerged arc welding systems. That means the welding robot runs along the entire seam, and the arc itself burns not in open air, but beneath a thick layer of special flux powder, stronger than the metal itself. After welding, our tank is one piece, but it's stressed out. Welding creates internal tensions in the metal that need to be relieved, so it's heading for heat treatment. A giant crane carefully lowers the entire 50-foot tank into a massive furnace. The doors close, and the temperature inside slowly climbs to 1,600 degrees Fahrenheit. It rests in that oven for about an hour. This process makes the metal more elastic and releases all the stress. Then the doors open, and out comes a red-hot monster, steam pouring off it. Workers in silver suits start hosing it down with water for controlled cooling. The air fills with a loud hiss, like 1,000 kebabs hitting the grill at once. I laughed and told the guys, "This is your sauna." Now for painting and coating. The cooled tank gets sent to a paint facility. This thing's the size of an aircraft hangar. Then comes the first layer, an epoxy primer that protects against rust. After that, 2 coats of top coat, white for better visibility on the road, and silver with added aluminum powder to reflect sunlight so the contents inside don't heat up. But what's on the inside? That gets special protective coatings. A thin but incredibly tough layer of polyurethane, just 10 millimeters thick. It's completely inert, doesn't react with fuel, and won't crack from vibrations. Workers use laser thickness gauges to check every square inch. No gaps allowed. Installing the fittings is the final touch that transforms the barrel into a high-tech tool. They mount the valves, fill valve on top, drain valve on the bottom, plus an emergency valve to release excess pressure. Each valve is a work of art made from stainless steel, rated for 200 pounds per square inch. They install electronic sensors for fuel level, temperature, and pressure. All the data feeds to a computer in the driver's cab. They mount an inspection hatch, 2 feet in diameter, with hermetic seals. I climbed inside an empty tanker myself, space like a space capsule, and absolute silence, because the 1/4-inch thick walls perfectly dampen sound. Testing, the most exciting and critical stage. First up, hydraulics. They fill the tank completely with water and pressurize it to 250 pounds per square inch. Inspectors with flashlights walk around it for 2 hours, hunting for even a single vacuum test. They pump out the air and check if the pressure drops. And the final, most precise test, pneumatics with helium. They fill the tank with pressurized helium, and special sniffer sensors check for the tiniest leaks. If not even a microscopic helium atom seeps through, the tank is ready for fuel. I watched them fill one test tank with 10,000 gallons of gasoline. Not a whiff of smell outside. The final stage, inspection and marking. A special plate gets stamped with a serial number, manufacturing date, and the empty tank's weight, 20,000 pounds. They slap on Department of Transportation certificates with all the safety specs. And then, a giant crane carefully lifts the finished gleaming tank and mounts it onto the truck chassis. Now it's ready to roll down the highway. Guys, this factory only produces 2 of these tanks per month. Each one's like a little mobile fuel fortress, incredibly safe and reliable. I'm absolutely blown away. From a simple steel sheet to a finished tank, every single detail is thought through. If you see these tankers on the road, know there's incredible work behind them. Thanks for watching. Hit that like button, subscribe, and I'll see you on the next factory tour. Today, I dragged you to a place so remote that cell service seems like technology from the distant future. And the main bosses here are massive excavators with wheels big enough to comfortably fit a small studio apartment. We're starting our journey at a nickel mine. Have you ever wondered where that perfect shine on a surgeon's scalpel comes from? Or why your pot doesn't turn into a pile of rust after cooking your first batch of borscht? The answer lies here, 1,600 feet beneath our feet. Nickel. This is the guy that makes steel tough and resistant to just about everything. But finding it? That's an adventure for the patient. Look at these numbers. To extract just 1 ton of pure nickel, miners have to move and haul to the surface about 100 tons of ore. That means the useful metal content in this rock ranges from 1 to 3%. Massive underground machines load up rock that looks like ordinary gray stone, but hidden inside is the promise of future strength. One of these dump trucks carries 240 tons of rock at a time. That's the weight of roughly 40 adult elephants, if you like those kinds of comparisons. After we've brought the ore to the surface, it's got a long journey ahead to the processing plant. There, the stone gets crushed into fine sand, washed, sifted, and turned into concentrate. It's not metal yet, but it's getting close. Then, and really hot. We're standing inside a shop where electric arc furnaces are doing their thing. Here, temperatures climb to 3,000 degrees Fahrenheit. That's roughly 10 times hotter than your home oven when you're trying to roast that holiday duck. All this molten metal churns like fiery soup, glowing so bright that without special goggles, you really shouldn't look at it. Not if you plan on seeing anything else for the rest of your life. Into the furnace goes scrap iron, that same nickel, and one more critical player. Chromium. Chromium is a whole story unto itself. For steel to officially earn the right to be called stainless, it needs at least 10.5% chromium. When this metal contacts oxygen, it forms an invisible, incredibly thin oxide film on the surface. It's so thin we can't even see it, but it becomes that impenetrable barrier that keeps the iron from oxidizing. So stainless steel doesn't rust. Not because it's magical, but because it's already coated with a protective layer at the atomic level. Once the steel melts, it goes through a procedure called argon-oxygen decarburization. Sounds like the title of a PhD thesis, but the idea is pretty straightforward. Surgical steel has to be incredibly pure and contain extremely little carbon. Too much carbon? It'll buddy up with the chromium, steal it away, and the steel loses its resistance to corrosion. A mixture of gases is blown through the molten metal under immense pressure, literally burning out the excess carbon while leaving all the useful additives in place. The whole process takes about 90 minutes. You can't rush this. One mistake in the proportions, and instead of a valuable medical instrument, you get ordinary rebar that'll be covered in rust spots within a few months. Next, this fiery liquid gets poured into continuous casting machines. Steel solidifies into long, massive strips that professionals call slabs. A single slab can weigh 20 tons and stretch about 40 feet long. When they come out of the machine, they're still glowing dark red, radiating so much heat you could toast bread in a fraction of a second without even getting close. Then these slabs head to the rolling mill. Picture a giant version of a rolling pin, except instead of dough, you've got a 20-ton chunk of red-hot steel. And instead of a baker's hands, you've got massive rollers pressing down on the metal with thousands of tons of force. The metal gets run through these rollers again and again, getting thinner and longer each time. From a slab 8 inches thick, steel workers produce coils of steel ribbon just a few hundredths of an inch thick. The speed at which steel flies through these rollers is an arrow racing through the plant. Now let's jump to a completely different place. Gone is the hellish heat and roar. We're at a medical instrument factory. The atmosphere here feels more like an operating room or lab, sterile, quiet, and fanatically detail-oriented. That steel ribbon we saw earlier, it's cut into small blanks. Then each blank is heated again, but now in small induction furnaces and forged in special dies. That's how the rough profile of a future clamp, forceps, or scalpel emerges. After forging, the real precision work begins. Craftsmen use grinding machines and hand finishing to perfect every curve. This is absolutely critical, because a surgical instrument must be perfectly smooth. Not a single burr or microscopic pit where bacteria could hide and multiply. The tolerances here are so tight they're measured in microns. A human hair is about 50 microns thick. We're talking about precision down to 5 or 10 microns. Once the instrument takes its final shape, it goes through heat treatment. It's heated to 2000 degrees, then rapidly cooled. This makes the steel hard, so the scalpel won't dull after the first cut, and the clamp won't bend in the doctor's hands. But after hardening, the metal becomes brittle, so it's heated again slightly, a process called tempering, to restore the necessary flexibility. One of my favorite stages is passivation. This is when the finished, already shiny instruments are immersed in baths of strong nitric acid solution. You'd think, why torture a finished product? But the acid does something really useful. It dissolves any microscopic particles of regular iron that might have gotten on the surface from the machines or the craftsman's tools. This cleaning allows that same protective chromium film we talked about at the beginning to become even thicker and stronger. After this treatment, the instrument can handle thousands of sterilization cycles in autoclaves at 273 degrees Fahrenheit under 2 atmospheres of pressure and stay shiny and clean for years. Let's crunch some numbers here, because they always help us grasp the scale of what's happening. The world produces about 50 million tons of stainless steel every year. If you stretch that metal into a thin wire, you could wrap our entire planet thousands of times. But only a tiny fraction of that steel, less than 1%, gets to become a surgical instrument. To manufacture one quality operating room set, you've got to process hundreds of tons of rock, burn through thousands of kilowatt hours of electricity, and run over 30 different quality tests. For instance, one ordinary surgical clamp passes through the hands of it lands in its packaging. Quality control here is so strict that a tool gets scrapped even for a microscopic scratch on the surface, something the naked eye wouldn't even notice without serious magnification. And here we see the final result, a tool weighing less than 2 ounces, but packed with the labor of thousands of people, from those who descended into dark mines for nickel, to those who calibrated the lasers for marking finished products. It's a long journey, where every step is a battle for quality and purity. Subscribe to the channel so you don't miss our next deep dives, because the world of manufacturing is way more fascinating than it seems at first glance. Thanks for watching, take care of yourselves, and choose only reliable tools for your life. See you in the next video. By the way, what do you think? Will humanity ever find a metal even stronger than today's steel alloys? Or have we already hit the peak of what's possible in this field? Every year, the world melts down more than 16 million tons of silicon metal, a material without which modern civilization would simply grind to a halt. It makes steel stronger, aluminum lighter, and solar panels possible. But here's something almost nobody knows. To create just 1 ton of this metal, furnaces operate at temperatures exceeding 5,400 degrees Fahrenheit and consume as much electricity as hundreds of American households use in a month. So why does this silent giant hide a diamond structure inside? And what discovery about silicon will change your understanding of technology if you stick around till the end? Industries use metallurgical-grade silicon as a foundational material for creating ferroalloys, particularly ferrosilicon, which gets added to steel to improve its strength, corrosion resistance, and ability to withstand high temperatures. How steel deforms, its elasticity and behavior under load largely depend on how silicon dissolved in the metal matrix behaves. Metallurgical silicon is also critical for producing aluminum alloys, where it's responsible for reducing weight and improving the alloy's ability to maintain its shape when heated. For example, in cast aluminum parts for automobiles, the silicon content can reach anywhere from 12 to 14% by weight. Another key application is obtaining purer silicon suitable for electronics and photovoltaics. Metallurgical-grade silicon serves as the starting point for producing polysilicon, which gets purified to impurity levels in the parts per billion range. This ultra-pure material is what they use to form ingots and wafers for microchips and solar panels. Demand in this sector has shot up dramatically in the US over recent decades, driven by renewable energy expansion, and a single solar panel module that's about 11 square feet requires roughly 6 or 7 pounds of silicon in the form of high-purity polycrystalline material. Metallurgical-grade silicon has additional applications too. It's used in chemical manufacturing to synthesize silicones, which are needed for sealants, lubricants, medical devices, household products, and electrical insulation components. It serves as the starting material for silanes, compounds that act as coupling agents between organic and inorganic materials, ensuring stronger surface bonding in composites. Certain types of silanes are used as part of adhesives and coatings that help extend the service life of structures in humid or corrosive environments. Technological progress constantly raises the bar for metallurgical-grade silicon, since purity, grain size, and consistency of properties directly impact the quality of the final product. In American industry, research continues on optimizing electric arc furnaces to cut energy consumption, as well as on utilizing carbon monoxide byproducts. On top of that, companies are developing ways to recycle silicon production waste to bring part of the material back into the cycle and reduce emissions tied to mining fresh quartz. All of this makes metallurgical-grade silicon one of the foundational industrial materials. Without it, modern electronics, transportation, and energy sectors couldn't keep up their current pace of development. To turn mineral oxide into metal, you need extremely high temperatures and a carefully controlled reduction reaction. This is done in large electric arc furnaces that operate at massive temperatures and consume enormous amounts of electricity. The furnace is loaded with crushed quartz along with carbon-based reducing agents. Most commonly, these are charcoal, coke, or various carbon briquettes, selected to ensure stable combustion and the right reactivity. Powerful graphite electrodes create an arc that heats the center of the furnace to approximately 5,430 degrees Fahrenheit. Under these conditions, ordinary rocks transform into active participants in the reaction. Silicon dioxide reacts with carbon, and as a result, oxygen is removed from the oxide. Gaseous carbon monoxide forms, while pure silicon transitions into a liquid state. The molten material is heavier than the surrounding charge, so it slowly settles to the bottom of the furnace, accumulating as a metallic mass. Once enough silicon is collected, it's released into special crucibles or troughs. As it cools down, the liquid metal solidifies into solid ingots, which are then crushed into smaller pieces that are easier to transport and process further. At this stage, it's crucisilicon. The raw material obtained at this point already has commercial purity of around 99%. This level of purity works fine for ferroalloys, but it's not enough for more demanding applications. Next comes the stage of refining the metal to higher purity. Silicon can be remelted in a vacuum or under an inert atmosphere, using various methods like sorption, zone melting, or chemical purification. The main goal here is to get rid of impurities like iron, aluminum, calcium, and sometimes phosphorus and boron. The impurity content is controlled with precision down to parts per million, because even a tiny amount of foreign elements can seriously affect the electrical properties of the final product. After purification, you get metallic silicon with the characteristics needed to produce alloys, silicones, or even purer polysilicon. The production process itself is energy intensive, so it's critical that the method ensures minimal heat loss and makes the most efficient use of electrical power. Modern furnaces come equipped with heat recovery systems and electrode feed control. This helps cut down overall energy consumption and boost productivity. Process optimization is a big deal here, because on average, making 1 ton of metallic silicon requires about as much electricity as several hundred American households use in a month. The quality of quartz sand plays a crucial role too. The purer the initial silicon dioxide, the fewer purification stages are needed after melting. Quartz with high impurity content can lead to increased energy consumption and greater furnace wear. That's why deposits supplying raw materials for the silicon industry must meet strict standards for chemical purity and mechanical uniformity of the material. Silicon, though it doesn't have gold's shine, is a true geochemical giant, an absolutely irreplaceable element. In terms of abundance in Earth's crust, it holds an honorable second place, losing only to a non-metal, oxygen. This means that, essentially, we live on a massive silicon-oxygen planet. It's hard to wrap your head around this, but this substance makes up a colossal 27.6% of our planetary crust's mass. Just imagine, almost every 4th ton of material we see beneath our feet is silicon or its compounds. It forms the backbone of entire mountain ranges and serves as the building material for countless minerals called silicates. This element isn't just filler, it's the foundation of our entire modern civilization. As a semiconductor, it powers every chip, processor, and transistor inside your phone, computer, and car. Abundant, but absolutely omnipotent. Its extraordinary purity is essential for microelectronics, making it one of the most demanding materials in the world. If you pick up any rock or handful of sand, you're holding an entire silicon factory. We all live on a massive silicon planet, not just a water one. Silicon could have been super expensive and sparkly, but it chose the humble path of being a semiconductor to run all the world's electronics instead. Why am I saying this? Because pure silicon has the exact same crystal structure as diamond. To put it simply, why silicon with the same structure as diamond isn't actually a diamond comes down to 2 key differences: atom size and bond strength. Diamond is made of carbon atoms, while silicon is made of silicon atoms. Plus, a carbon atom is tiny, whereas a silicon atom is much bigger. Even though both elements form the same spatial lattice, silicon atoms, being larger, force the whole structure to expand. This makes the bonds between them longer and, as a result, weaker. We're standing at a modern asphalt plant. It smells like hot tar, heated stone, and a little bit of my morning coffee, which I nearly spilled when I saw the scale of this metal structure. Most people think asphalt is just some black goop they smear on the road, but it's actually a whole science where every pound and every degree matters. We're about to break down this process into parts and see how a pile of rocks and a barrel of sticky liquid turns into a perfectly smooth highway. It all starts at the aggregate storage yard. These are massive mountains of crushed stone and sand you see behind me. This is serious business. The rocks are sorted by size. We've got really fine screenings, and we've got fractions half an inch or even 3/4 of an inch. Why does this matter, you ask? Because asphalt is like a cake. If you put in too many big nuts and not enough flour, it'll just fall apart under your car's wheels. A special loader grabs this crushed stone and dumps it into huge steel bins. Each container holds about 10 or 15 tons of material. Then begins a long journey on a conveyor belt. This rubber track stretches for dozens of feet and carries the stone to the heart of the plant, the dryer drum. Look at this giant metal tube slowly rotating. It's about 30 or 40 feet long. Inside it, a real flame roars. Why do we roast stone? Because there can't be a single drop of moisture in it. If water gets into the hot mix, it'll turn to steam and punch holes in your future asphalt, what we call voids. The temperature inside this drum climbs to 300 or even 350 degrees Fahrenheit. That's way hotter than your oven when you're baking pizza. Once the stone is properly roasted, it becomes super hot and bone dry. Now it needs to be lifted to the very top of the plant. They use an elevator for this, a vertical chain with buckets that stretches up 60 or 70 feet. Up there at the top, the scorching aggregate gets screened again through a set of sieves. It's like a final quality check to make sure no random wrong-sized rock messes up our road. Now we get to the star ingredient, bitumen. That's the same black sticky stuff that holds all the stone together. It's stored in massive vertical tanks that are constantly heated. If the bitumen cools down, it becomes hard as a rock, and we can't do anything with it. Each of these drums can hold up to 20 or 30,000 gallons of this black liquid. The bitumen is fed into the mixer under high pressure. It looks pretty epic, although peeking inside while it's running is a bad idea, unless you want to become part of the road. The actual mixing process happens in a giant mixer. They dump in a precisely measured amount of hot stone, add mineral powder, think of it like cement dust for thickness, and pour in the liquid bitumen. One mixing cycle takes about 40 or 50 seconds. In that short time, the mixer blades have to coat every single grain of sand with a thin layer of black gold. Imagine the responsibility. If you mix it poorly, the asphalt will start crumbling after the first winter. The finished asphalt comes out of the mixer at around 320 degrees Fahrenheit. It's basically molten black lava. From there, it either gets dumped straight into a dump truck bed, or it heads to a storage silo. These silos look like space rockets sitting on a launch pad. They can hold 200 to 300 tons of hot mix for several hours while maintaining temperature. This lets the plant run non-stop, even when trucks get stuck in traffic jams. I'm standing right now at the control panel. People sit here watching every pound of weight and every degree of heat on their monitors. A modern plant is a fully automated system. The operator just enters the recipe, and the computer decides how much sand, how much aggregate, and how much bitumen to mix. This eliminates human error, because a mistake of 0.1% in the formula can cost millions if the road has to be redone a year later. You've probably heard that asphalt is one of the most recyclable materials in the world, and it's true. This plant has a special unit for adding old asphalt that's been milled off other roads. They grind it up and put it back to work. It's awesome because we're not just tossing old rocks into a landfill, we're giving them a second life. The recycled material can make up 20 or even 30% of the new mix. That's good news for the environment and for the builder's wallet. Let's just take a quick detour right now and peek at how this goes down. Dawn breaks. The highway's blocked off with orange cones, and there's this thick steam rising from the hot asphalt. Feels like we're on the set of a volcano eruption movie. Our dump truck slowly backs up to the paver. This massive iron-tracked machine worth close to $500,000. The truck bed lifts, and 20 tons of black, steaming mass at 300 degrees Fahrenheit pours straight into the receiving hopper. Inside the paver, powerful augers are at work. Giant screws, just like the one in your meat grinder at home, only 12 feet long. They spread the hot mix evenly across the entire width of the lane. Behind the machine comes the screed plate, which doesn't just level the asphalt. It vibrates with crazy force to compact it initially. The machine leaves behind a perfectly smooth, black-as-night carpet, but it's still too soft. Step on it now, and your shoe stays there forever. And that's when the heavyweights enter the scene. The rollers. First comes the vibratory roller, weighing about 10 or 12 tons. Its steel drums rotate while simultaneously pounding the road at a rate of 40 or 50 strikes per second. You feel this vibration even through the soles of your sneakers from 30 feet away. This is necessary to squeeze out all the air and make the pavement solid. Behind it rolls a pneumatic tire roller on rubber wheels. It smooths the surface, sealing the tiniest pores so water can't get in. One pass after another, and we get a road that'll last 15 or 20 years. Let's go back to the plant. Another interesting point is air cleaning. You see that big box next to the drying drum? That's a baghouse filter. Inside it are hundreds of long fabric bags that capture dust. Only clean water vapor goes into the air, and all the dust is collected and goes back into the asphalt. So stories about these plants being super dirty, that's ancient history. Modern production is cleaner than the kitchen in most fast food restaurants. Now about volumes. A mid-sized plant like this can put out around 240 tons of asphalt per hour. Just to put this in perspective, that's roughly 12 big rigs worth of material. In a single 10-hour shift, this metal giant produces enough asphalt to lay several miles of new 2-lane highway. That's insane speed and massive responsibility. When a dump truck pulls up under the hopper, about 20 tons of smoking black mass pours onto it. Then the driver covers the bed with a special top so the asphalt doesn't cool down on its way to the paving site. If the temperature drops below 250 degrees Fahrenheit before it gets rolled out, you won't get a quality road. So logistics here is a real race against time. Watching one of these plants operate is like watching a really big, really complicated food processor. Nothing here is wasted. Every motor and every sensor performs its exact function. And while from the outside it looks like a pile of smoking, rumbling metal, it's actually a triumph of precision and engineering calculation. Every mile of highway we drive on vacation or to work started right here, in this hot, noisy place. Stick with me. We've got plenty more fascinating machinery and weird mechanisms coming up that make our lives more comfortable, even if we usually don't notice them. What if the metal that still powers most cars on the planet has been quietly poisoning people since the days of the Roman Empire? And we found out too late. Lead built aqueducts, adorned the faces of Egyptians, and today hides in billions of lead-acid batteries, without which cars, elevators, and entire cities would grind to a halt. We'll descend into mines where explosives shatter rock, trace the journey of galena to red-hot furnaces, and discover why this metal simultaneously saves infrastructure and destroys health. Stick around till the end. One fact about lead will forever change how you look at an ordinary battery. Okay, let's rewind the clock and dive into a story that began long before the first smartphones and even before the invention of the wheel. How did people even learn about lead, this sneaky, two-faced metal? Truth is, nobody knows exactly who or when first discovered lead, because it wasn't officially discovered by a scientist in a lab like many other elements. Lead is one of those metals that's just always been around humans, and its history is intertwined with the history of civilizations themselves. Picture this: ancient times, way before people learned to work with iron, or even copper. They were searching for interesting stones, clay, anything they could use. And then, in certain places, especially where there are ore deposits, they stumbled upon a really unusual stone. These were lead ores, most commonly galena, lead sulfide, which looks like dark gray, almost black crystals with a metallic shine, often in cubic shapes. Lead ores often lay close to the Earth's surface, and there was plenty of it around. Plus, lead sometimes occurs in its natural, pure form, though that's pretty rare. Lead has an incredibly low melting point, just 621 degrees Fahrenheit. This means you didn't need some super high-tech furnace to melt it down. A good hot campfire was enough, and if there happened to be lead ore nearby, shiny liquid metal could literally just melt right out of it. The metal in the ore heats up, melts, and starts flowing out of the rock, forming little shiny puddles or droplets. This must have been absolutely mind-blowing to witness. Out of stone, without any tools, just from fire alone, this shiny, heavy, soft material appears that you can shape with your hands. You could easily flatten it, bend it, cut it even with primitive tools. It wouldn't break like stone. This made it perfect for crafting simple objects. Archaeological findings show that lead was used as far back as 7,000 or 8,000 years ago, dating to the Neolithic period, for example, in Turkey. People found beads and other small lead objects there. In Mesopotamia, Egypt, and later in Greece and Rome, lead became widespread due to its availability and ease of working with. The Romans built their famous aqueducts and water supply systems using lead pipes. The word plumbing comes from the Latin plumbum, which means lead. Ancient Egyptians used lead sulfide for eye makeup, while Romans used it for skin lightening and in paints. Nobody back then, of course, suspected this metal was toxic. After all, lead poisoning symptoms were often chronic, developed slowly, and could easily be blamed on bad luck, other illnesses, or curses. People just saw a shiny, useful metal that was easy to work with, and they actively used it, never suspecting that beneath its appeal lurked a treacherous enemy. Now that we know the grim history of lead's discovery, let's fast forward to our time. Despite all its toxicity and the massive campaign to phase it out, lead is still part of modern industry. But how is it mined now, and where does it hide when we're so desperate to get rid of it? This is a story about precision, control, and the constant battle against its poisonous nature. Lead, like its neighbor zinc, is rarely found in its pure form. It's mostly extracted from ores, where it exists as lead sulfide, known as galena. And, as you might have already guessed, this anti-hero often shares its deposits with zinc, as well as other valuable metals like silver and copper. The world's top lead producers are China, Australia, the United States, and Peru, which once again overlaps with the geography of zinc mining. The extraction process starts with locating ore bodies. Geologists, armed with cutting-edge technology, scan the ground and conduct exploratory drilling to find spots where galena concentrations make economic sense. Once a deposit is identified, mining operations begin. This can either be an open-pit mine, where massive excavators strip away the top layers of earth, gradually working their way down to the ore, or an underground mine, where miles of tunnels are drilled, penetrating deep into the Earth's crust. In underground mines, drilling rigs are used to create holes in the rock, which are then packed with explosives. After controlled blasts that break up the ore vein, specialized loaders gather the ore fragments and haul them to the hoisting shafts. Ventilation systems run at full capacity, removing dust and pumping fresh air down into the depths. All the ore is brought to the surface, where it begins its long journey to becoming a metal ingot. After crushing, the flotation process kicks in. This is a chemical-physical method that separates different minerals. The crushed ore is mixed with water and special reagents in massive tanks. These reagents selectively attach to galena particles, making them water-repellent. Then air is pumped through the mixture, creating bubbles that the lead mineral particles cling to and rise to the surface as foam. This foam is collected, forming lead concentrate. The waste rock settles at the bottom and gets disposed of. Since lead and zinc are often found together, different reagents and flotation cycles can be used to separate them individually, which requires high precision and chemical control. The resulting lead concentrate, now containing a much higher percentage of lead, is shipped to the metallurgical plant. This is where it transforms into pure metal. The most common method is pyrometallurgy, which involves several stages. First, the concentrate is roasted in special furnaces at high temperatures. This is a calcination process that removes sulfur from galena, converting it into lead oxide. The sulfur that's released as sulfur dioxide gas is carefully captured and converted into sulfuric acid to prevent air pollution. Then the lead oxide is loaded into large blast furnaces, where it's mixed with coke and fluxes. In these furnaces, at temperatures over 2,000 degrees Fahrenheit, a reduction process takes place. The carbon from the coke pulls oxygen away from the lead oxide, releasing liquid metallic lead. The molten lead, which is extremely heavy, settles to the bottom of the furnace. On top, a layer of slag forms. That's the melted impurities. Molten lead is periodically drained from the furnace, but this isn't pure lead yet. It contains impurities of other metals, such as copper, silver, gold, bismuth, and nickel. That's why lead goes through one more stage, refining. This could be heating to specific temperatures to remove impurities, or electrolytic refining, where electric current separates lead from other metals, achieving very high purity. It's at this stage that valuable byproduct metals like silver and gold, which accumulate in lead ores, are extracted. So where is all this carefully mined and refined lead being used today, now that we know about its dangers? The biggest consumer of lead, accounting for about 85% of all global consumption, is the production of lead-acid batteries. These are the same batteries that start the engines in nearly every car on the road, and they're also used in uninterruptible power supplies, backup power for telecom networks, and large-scale energy storage systems. In electric vehicles, even though the main battery is lithium-ion, there's often still a small 12-watt lead-acid battery to power the onboard electronics. This is a massive market that keeps demand for lead rock solid. Every year, the world builds hundreds of miles of underground tunnels, but almost nobody thinks about what's holding them up above our heads. Picture this: thousands of concrete segments, each weighing several tons, assembled with precision down to the millimeter, forming tunnels where trains blast through at dozens of miles per hour. Now here's the big question: what happens if even one of them is made wrong? Today, we're diving into the place where the backbone of the subway is born, where one tiny mistake can cost millions or more. But there's a detail they usually don't show. Stick around till the end, and you'll find out what's actually hidden inside these concrete rings. Let's start with what a tunnel lining segment is, and why we need it. When a tunnel boring machine grinds its way through soil, you've got to shore up the tunnel walls right behind it, because soil isn't rock and won't hold itself up. The shield pushes forward, and behind it, installers assemble a ring from several segments, usually 5 to 8 pieces plus one keystone. The assembled ring is what you see when you're riding the subway and looking out the window. Uniform concrete sections with bolted connections along the seams. Looks mundane. Actually, an engineering solution refined over more than 150 years. The plant I visited manufactures tunnel segments for the city subway. Tunnel diameter, 21 feet. Each ring consists of 6 segments and 1 keystone. Width of one ring along the tunnel axis, 5 feet. Concrete wall thickness, 18 inches. One segment weighs close to 4,500 pounds. Monthly, the plant ships out about 600 rings, meaning over 4,000 segments. The math comes out monumental. It all starts with rebar cages. This is the exact moment when steel rods transform into a 3-dimensional structure that'll end up inside concrete and keep it from cracking under load. The rods get cut and bent on automated lines. The machine receives a program, selects the right wire diameter, bends it at the specified angle, and cuts it to size. The thinnest rods here are about 1/4 inch in diameter, the thickest around 1 inch. Then the cages are assembled by hand or welding. It's tedious and monotonous, and workers here are clearly grateful when automation handles the whole process. The finished cage gets placed into a steel mold. The mold is probably the most expensive thing in these entire factories after the presses themselves. It's manufactured for a specific project and specific tunnel diameter. One mold costs anywhere from $200,000 to $400,000, depending on the complexity of the geometry, and it's rated for several thousand cycles. Before each pour, the mold gets cleaned of leftovers from the previous cycle and coated with special release compound. Without it, concrete bonds to the steel permanently, and you can't pull the segment out without damage. The lubing process is its own science. Too much creates pores on the concrete surface, too little ruins the mold and wrecks the piece. Seems minor, but at the plant, they train people separately just for this. Next, concrete. They don't pour regular batch plant mix here. Segments get made from special grade concrete with precisely dialed in water cement ratios, aggregate size, and additives. Compressive strength, not less than 6,000 pounds per square inch. For comparison, concrete in typical residential construction runs around 3,000. This stuff is twice as dense and heavy. Additives in the mix ensure waterproofing, because subway tunnels run below the water table, and the concrete has to hold water back completely, not soak it up like a sponge. The mix is prepared in an automated plant right at the factory and delivered to the form by transport conveyor or buckets. They don't pour the entire form at once. They do it in layers with vibration in between. Vibrators plunge into the concrete, and when switched on, the vibrator squeezes out air bubbles from the mix. If you leave air in, the concrete will have voids, and porous concrete lets water through and is less strong. One segment takes anywhere from 45 minutes to an hour, accounting for all the layers and vibration. Rushing here is harmful. This is one of those cases where slower actually means better. The filled form heads into a heat treatment chamber. Steam curing, that's what it's called. The temperature inside, around 100 degrees Fahrenheit, humidity high. The goal, speed up cement hydration and let the concrete gain sufficient initial strength in 8 to 10 hours, instead of the standard 28 days. After curing, the concrete has about 70% of its design strength, enough to remove the formwork without risk of damaging the product. Demolding, the moment I hold my breath a little every time. The crane operator lifts the top part of the mold, then the side panels swing away, and the segment stands on its own. A concrete arc that was just a sloppy mix 8 hours ago. Looks solid. No wonder. 14,000 pounds of solid concrete with rebar in the center. Next, the segment gets moved by crane to a curing rack, where it'll sit for another 7 to 14 days, until it reaches full design strength. Quality control runs parallel to all this. And it's serious here, because tunnel segments aren't paving stones. Each piece gets marked and assigned a unique identification number. During the pour, they pull test cubes, small concrete cubes measuring 4 by 4 inches, that later get crushed in a press to measure the actual strength of the batch. At the same time, ultrasonic testing of finished segments. The ultrasonic device presses against the surface and measures the speed of the wave passing through the concrete. Dense, uniform concrete gives one reading, concrete with hidden cracks or voids, another. The difference shows up immediately, and that segment gets rejected. Another type of control is geometric. Each segment gets placed on a measurement stand, and all key dimensions get checked. Arc length, thickness, bolt hole positions, surface flatness. Bolt hole tolerance can't exceed 1/32 of an inch. Segments that fall outside tolerances, and it happens more often than manufacturers are willing to admit publicly, either get sent back for rework or scrapped. On large projects, the rejection rate can run anywhere from 1 to 3% of total output. Doesn't sound like much at first, but when a single segment runs $4,000 to $6,000, it adds up fast. A separate curiosity, the waterproofing profile. Around the perimeter of each segment, there's a special groove. A rubber gasket fits in there. When the segments get compressed by bolts into a ring, the rubber deforms and hermetically seals the joint. This rubber profile looks like an ordinary black strip, gets manufactured from a highly specific compound based on chloroprene rubber, withstands pressure up to 120 pounds per square inch, and lasts as long as the tunnel itself, meaning it's designed for a minimum of 100 years. Rubber that'll outlive you and me both. Bit philosophical. Shipping from the factory isn't exactly simple either. The segments are heavy, fragile around the edges, and demand careful handling. They're loaded onto specialized frames, secured with tie-downs, and a flatbed truck hauls them to the construction site. There are limits on stacking height, no more than 3 tiers, because the bottom segments can't take excessive weight from above. At the construction site, they dig a vertical shaft. The segments get lowered underground and assembled into rings right behind the shield as it pushes forward. The shield advances 5 feet, the width of one ring, and the crew installs the next one. This rhythm never stops, day or night. I step out of the plant and stop beside a stack of finished segments. Gray, slightly rough, smelling of cement. Totally unremarkable. In a few weeks, they'll be 50 feet below city streets, just sitting there. As long as the city stands. No days off, no maintenance, no attention whatsoever from the people above them. That's the fate of a concrete arc weighing 4,000 pounds. I'd complain, but the concrete doesn't seem to mind. See you on the next tour. 70% of the plastic you toss in the recycling bin ends up straight in a landfill. Not because you're doing something wrong, but because traditional recycling only wants clean, single-type plastic. Everything else, dirty packaging, films, toys, shoe soles, not its problem. But there's a technology that takes any dirty, mixed plastic and turns it back into oil. No burning, no oxygen. I just visited one of only 25 facilities like this in the entire world, and I'm going to break down exactly how it works. From a pile of trash to a barrel of synthetic oil. Plus, one number from the director that makes it crystal clear. Even this is just a drop in the ocean. Regular plastic recycling, the kind you know from those triangle bins, it's super picky. It wants plastic to be one type, clean, no caps, no labels, no food residue. Plastic bottles, separate. Polyethylene, separate. Polystyrene, they often refuse to take it at all. And anything that doesn't meet these criteria, which is roughly 70% of all plastic that ends up in the trash, goes straight to the landfill, or gets burned. All that dirty food plastic, multi-layer chip bags, toys, shoe soles, films, traditional recycling doesn't want them. And that's where a different game begins. What they do at this facility is called chemical recycling, or plastic pyrolysis. And the principle is so simple, at first you don't even believe it. They take plastic and heat it without oxygen to temperatures between 550 and 900 degrees Fahrenheit. At that temperature, the long polymer chains, and plastic, if we're being brief, is just very long chemical chains, break apart into short fragments. These fragments escape as vapor, enter a condenser, cool down, and turn into liquid. This liquid is pyrolysis oil, or synthetic crude oil, the exact same product that's the starting point for making plastic, gasoline, chemicals. The circle is complete. But the gap between theory and what happens here in practice, wide as Texas. First problem, raw materials. The plant processes anywhere from 150 to 200 tons of mixed plastic every single day. I saw this pile. It looks like where all your plastic bags, disposable lids, and thermos caps go to die. Before any of this hits the reactor, it goes through sorting, cameras, magnets, air separators. Metal has to come out completely because it just won't break down in the reactor and it clogs the equipment. Chlorinated plastics, for example, have to be separated out because when heated, they release hydrogen chloride, which literally eats the reactor from the inside. One poorly sorted container can shut down the entire line for days and cost the plant tens of thousands of dollars in repairs. After sorting, the plastic gets cut into pieces roughly 1 inch by 1 inch. This ensures even heating in the reactor. The shredders here are the size of a bus and chew through everything with a sound that makes you want to jam in earplugs and drive home. Then these pieces get fed into the reactor by an auger conveyor. The reactor, that's the key piece, and all the complexity revolves around it. It's a massive steel cylinder. This facility has 6 of them, each as tall as a 3-story building. And inside, a complete absence of oxygen is maintained. This is critical. If oxygen gets in at these temperatures, you won't get pyrolysis, you'll get ordinary combustion. Basically, a fire inside. That's why before feeding in the plastic, the system is purged with nitrogen, replacing the air with an inert gas. Oxygen sensors are mounted on every flange, and if the level rises above 0.5%, the line shuts down automatically. At 750 degrees Fahrenheit, polymer chains start breaking apart. Polyethylene, polypropylene, polystyrene, they all have different cracking temperatures, different reaction rates, different product yields. That's exactly why mixed plastic is so tricky. If you fed only pure polyethylene into the reactor, you'd get a stable 80% oil yield by weight of feedstock. With mixed plastic, that number bounces between 50 and 65% depending on batch composition. And there's no way to predict more accurately without chemical analysis of every ton. And that kind of analysis costs money. Real money. The vapor coming out of the reactor is a mixture of hydrocarbons of different sizes. It passes through a fractionation column where it separates by boiling point, almost like at a regular oil refinery. The lightest fractions are gases. They don't condense and get burned immediately in a burner to produce heat that's fed back into the reactor. At this stage, the plant is practically energy self-sufficient. It heats itself with its own gases. The middle fractions remain as pyrolysis oil, a dark, slightly viscous liquid that smells roughly like you threw a plastic bottle on a campfire and let it burn completely. The heavy fractions settle out as fuel oil or a waxy substance. And there's still a solid residue left over, carbon black or technical carbon. It gets pressed into pellets and sold to manufacturers of rubber products or pigments. There's another technical hurdle worth explaining: chlorine. Chlorine actually hides in a ton of different packaging, in dyes, additives, adhesives. When plastic with chlorine gets into the reactor, the chlorine reacts with water and forms hydrogen chloride, an extremely aggressive acid. It eats through the steel reactor walls from the inside in about 6 to 12 months instead of the projected 10 to 15 years. Replacing a single reactor costs several $1,000s and weeks of downtime for the entire production line. So chemical analysis of incoming plastic and chlorine monitoring is literally a matter of plant survival. While I was walking through the facility, one detail struck me: sensors everywhere. On every pipe, every valve, every welded joint, there are sensors for temperature, pressure, and gas composition. This entire system feeds into a central control room where 3 operators watch screens displaying roughly 300 parameters simultaneously. If pressure in any reactor jumps above the calculated value by more than 5%, an automatic valve releases the excess. If temperature drops below 2.5 degrees, cracking quality decreases and the oil comes out heavier. That's bad. If the temperature exceeds 900 degrees, gasification kicks in, oil yield drops to 0, and all you get is gas and carbon. The window between normal and something went wrong? Literally 50 degrees. In a reactor the size of a house. The pyrolysis oil produced here gets shipped in tankers to petroleum refineries, where it's blended with regular crude and goes through cracking, turning into naphthene and xylene, which are feedstocks for making new plastic. So theoretically, a shampoo bottle could circle back to polypropylene pellets and become a new bottle. Some major chemical companies, including several from the global top 10, are already buying this oil to manufacture plastic, and even paying a premium over conventional petrochemical feedstock, because they can print "made from recycled plastic" on the packaging, and for them, that's a marketing asset. The plant director told me straight up that even if they double their capacity and hit 400 tons a day, they'll be processing less than 0.1% of the world's plastic waste stream. The solution to the problem? Either drastically cut plastic production or build several thousand of these plants across the globe. Right now, neither is anywhere on the horizon. But this plant is proof that mixed plastic pyrolysis technology can actually work at industrial scale and turn a profit, even if it's razor-thin margins with really nerve-wracking logistics. I'm walking out of here with respect for the people doing this work, and a solid sense that 92%? That number's going to stay relevant for a long time. And you know what else is going to stay relevant? Subscribing to my channel. In every country, asphalt is just a road. But in Dubai, it's a challenge to nature. Here, air temperatures reach 122 degrees in the shade, while the road surface heats up to 160. Regular asphalt would melt within just a few days, but engineers found a way to make it survive. Polymers that hold their shape even at 176 degrees, geotextile membranes that breathe, and sensors that detect defects before human eyes can spot them. Why don't these roads melt like ice in the sun? And what strange technology did they test to make them actually dry after rain? Watch till the end. The finale will surprise you. Standard asphalt consists of stone aggregate and bitumen, a dark, thick substance that holds the mixture together, making it uniform and strong. However, bitumen has one weakness. It starts to soften at temperatures around 113 degrees Fahrenheit. For countries with moderate climates, this isn't a problem since road surfaces rarely reach such heating levels. But Dubai has completely different conditions. There, summer air can heat up to 122 degrees in the shade, while the road surface under direct sunlight can reach 160 degrees. Under such conditions, regular asphalt would literally behave like warm rubber. It would become soft, start deforming under vehicle weight, and in places simply slide off slopes. Plus, sharp temperature changes between scorching days and relatively cool nights would cause cracks to appear. In countries where occasional short heat waves occur, people might not immediately notice these processes. Sure, we sometimes get 104 degrees in summer, but such temperatures don't last long, and the surface deteriorates slowly, gradually. In Dubai, however, high temperature isn't just present, it's constant and stable for several months. This means asphalt is under continuous stress, and if you don't account for this factor, the road literally won't survive. That's exactly why engineers had to find a solution that would allow asphalt to maintain its shape even under extreme heating conditions. They replaced regular bitumen with modified bitumen, with polymer additives that change its physical properties. Such bitumen holds its shape at temperatures up to 176 degrees Fahrenheit. This means even when the road surface heats up to maximum levels, the material still remains stable, doesn't flow, and doesn't change structure. The difference might seem small at first glance. What's a few dozen extra degrees? But this exact difference makes Dubai's roads smooth, even, and durable, even when it's almost impossible to breathe from the heat around you. So what is this modified bitumen? The process is based on mixing bitumen with polymer additives. Polymers act like a reinforcing network at the molecular level. They stretch the bitumen structure, making it more elastic and heat-resistant. As a result, the asphalt doesn't soften. It maintains stability and shape even when heavy bus or truck wheels press on it for hours. The mixing process also isn't limited to just adding polymers. It's crucial to properly select the stone aggregate composition. Stones of different sizes create a framework-like structure, and bitumen here acts not as the main material, but rather as what connects the elements together. If the aggregate is selected incorrectly, bitumen will have to take on too much load, and even the modified mixture will lose stability. Therefore, asphalt composition is always a precise calculation of material ratios that don't just connect, but work as a unified system. But asphalt is just the surface. Hidden beneath it is a multi-layered sandwich that determines the road's durability. The first layer is sand, but regular sand won't work. It's mobile, can shift, and the road would lose its evenness within months. So sand is stabilized by mixing it with cement or special substances that make the mixture less mobile. Next comes a crushed stone layer that provides hardness and distributes load. Special geotextile fabrics can be laid between layers, preventing settling and material mixing. Geotextile works as a membrane that allows water to pass through, but doesn't let soil particles mix. This keeps the construction stable for many years. The way asphalt is actually laid also plays an important role. Work is usually done at night when temperatures are lower. This is necessary so bitumen cools evenly and gains the required hardness. If you lay asphalt during daytime heat, its surface will cool unevenly, creating stress in the structure that will eventually lead to microcracks. After laying, roads are regularly checked using special machines equipped with sensors and thermal imaging cameras. If sections are found where temperature is too high or irregularities appear, they're repaired immediately, not waiting until the problem becomes visible to drivers. Experiments with cooling coatings deserve special mention. In some districts, asphalt is painted or covered with a special compound that reflects sunlight and reduces surface heating by 10 to 15 degrees. This is important in pedestrian areas since road surface temperature affects how hot the air gets at foot level. This way, even a regular walk becomes less exhausting. In Dubai, roads aren't left unattended until large potholes appear. Control happens constantly and systematically. Special vehicles with measuring equipment travel highways and city streets, recording the smallest irregularities. Sensors read surface deviations, and computers compare them to standards. If there's suspicion of overheating or beginning deformation, the section is checked with thermal imaging cameras. High temperature indicates that bitumen is losing rigidity, and the surface might start settling. Thanks to such monitoring, repairs are done not when it's too late, but when the first changes begin. Repair work is conducted mainly at night when temperatures are lower and material cools evenly. This extends the road's service life and avoids repeated damage. The approach is based on the idea that infrastructure should work continuously, not wait for the moment when it becomes a problem for drivers. According to Dubai municipality data, after switching to polymer-modified mixtures, the number of deformation waves on roads decreased by approximately 40% during the first 2 years. Meanwhile, road surface service life increased on average from 7 to 10 years to 12 to 15 years before the first major repair. This significantly reduces overall infrastructure costs. Although initial polymer asphalt installation costs are higher by approximately 15 to 20%, long-term savings can reach 50% due to reduced repair needs. There's also data on experimental light reflective coatings being tested in residential areas and near pedestrian zones. On average, such coatings reduce road surface temperature by 10, or even all 14 degrees, depending on conditions. According to observations, in areas with cooling roads, air temperature at pedestrian foot level also drops by 2 to 3 degrees, reducing thermal load on people and making outdoor stays more comfortable. Statistics also show that, with early detection of surface microdefects, their elimination takes on average 3 to 6 hours, while if you wait for visible damage to appear, repairs can last from several days to several weeks and require closing road sections. Therefore, the city focuses on regular monitoring. In 1 month, control vehicles can cover over 80% of the city's road network. Dubai once tested asphalt that absorbs solar energy, then radiates stored heat at night to dry roads faster after rare rainfall. Turns out, the surface works like a giant thermos. During the day, it accumulates energy, and at night gradually releases it. The experiment showed such roads can dry 30% faster. And this is really needed, because after desert rain, water doesn't absorb into the ground, but can stand on asphalt for hours or even days. So the technology solves a problem that doesn't even exist in most countries. You know how this experiment ended? Today, I dragged you out to a place where dust isn't a sign of bad housekeeping. It's the smell of serious money and the foundation of everything we call civilization. We're at a cement plant. Look at this landscape. It's like we just landed on Mars, except instead of red sand, everything here is coated in a fine layer of gray powder. Just think about it. We produce over 4 billion tons of this stuff every year. If you tried to stack it all up, you'd get a mountain that would dwarf any skyscraper in New York. We start our journey at the very beginning, the quarry. Just look at these machines. These giant dump trucks look like they escaped from a Transformers movie, but instead of saving the world, they just haul limestone all day long. One wheel on this thing stands about 12 feet tall. That's twice the height of your average pedestrian, who's probably sipping a latte somewhere downtown right now, completely unaware that their apartment is held up by the efforts of these steel monsters. Limestone is the foundation of everything. It's ancient shells and skeletons of sea creatures that decided to die right here millions of years ago, so we could build another shopping mall today. When limestone gets blasted in the quarry, chunks of rock can be the size of a compact car. But for the plant, that's way too coarse. That's where the primary crusher comes in. It's this massive steel jaw that chews through rock as easily as you crunch chips in front of the TV. The noise here is so intense that your noise-canceling headphones would just give up and retire. After the crusher, we get chunks no bigger than 3 or 4 inches. Next, all this mass goes onto a conveyor belt that stretches for miles. It looks like an endless snake crawling through fields and roads straight to the heart of the plant. Now we enter the raw materials prep shop. This is where the cooks of the industrial world mix their secret recipe. Besides limestone, we need clay, sand, and a bit of iron ore. All of this has to be ground into a fine powder called the raw mix. You can't even imagine how precise this ratio has to be. The lab checks the composition every 15 minutes. If they're off by even 1%, your entire skyscraper might just decide it'd rather lie down than stand up. Chemistry rules everything here. It's pure science, where we make molecules dance to our tune. And now brace yourselves, because we're approaching the hottest spot on the map. This is the rotary kiln. If you ever thought summer in Texas was hot, you knew absolutely nothing about life. This kiln is a gigantic steel tube over 600 feet long. It's tilted at a slight angle and constantly rotating. Inside, it's straight up hell. Temperatures in there climb to 2,700 degrees Fahrenheit. That's so hot that iron starts to weep. At this moment, what we call decarbonization happens. The limestone breaks down, releasing carbon dioxide, and transforms into calcium oxide. This is the moment of truth. The raw material begins to melt and clump into little gray balls called clinker. Clinker is basically a semi-finished product, cement in its embryonic state. Just think about the energy needed to keep a fire like that going. They burn everything here, from coal to old car tires. So, here's something wild. Old tires make excellent fuel because they burn completely at these temperatures, leaving behind nothing but energy for our kiln. It's like nature's own brutal recycling program. When this red-hot clinker exits the kiln, it looks like tiny meteorites that just fell from the sky. It needs to be cooled immediately. Massive fans blast it, dropping the temperature from thousands of degrees down to 160 degrees Fahrenheit in just minutes. The whole thing looks incredibly dramatic. Clouds of steam, glowing metal, and that distinctive crackling sound. But this still isn't cement. The final stage is the last grinding. We take our clinker, add a bit of gypsum to it, about 5% of the total weight, and send it into a ball mill. This is another horizontal tube, but inside it's packed with thousands of steel balls. As the tube rotates, these balls drop and pulverize the clinker into such a fine dust that it becomes softer than the flour your grandma uses to bake pies. The gypsum here is needed, so the cement doesn't set instantly when you add water to it. Without gypsum, construction workers simply wouldn't have time to carry a bucket of mix to the wall. This grinding process is incredibly loud and consumes enough electricity to power a small town. But the result is worth it. Now we have a gray powder that can turn into stone on command. We store it in massive silos, these concrete towers that can reach up to 150 feet tall. Each silo holds thousands of tons of finished product. Look at these trucks lined up in queue. They haul this powder all across the country. Rail cars, barges, bags at hardware stores. Cement is everywhere. Every American indirectly consumes close to 1,000 pounds of cement each year. We literally live inside this material. Our roads, bridges, building foundations, even power plant dams. All of it depends on those gray granules we just saw inside that blazing kiln. People often tell me this is a dirty business. And yeah, it's true. There's no cement without dust and fire. But that's where its raw beauty lies. This is an industry that doesn't tolerate weakness. Everything here is massive, everything scorching hot, and everything operates at the physical limits of what materials can handle. It's a real battle between man and matter, where we force solid rock to go liquid, then solid again. But this time in exactly the shape we need. Next time you're walking down a sidewalk or staring up at bridge supports, remember the long journey that stone took. From an explosion in a quarry to 2,700 degrees inside a kiln to steel balls in a grinding mill. It's a long road, packed with chemical transformations and incredible engineering genius. We've learned to control processes that took nature millions of years to create, and we're doing it at a scale of billions of tons. I hope you enjoyed this journey through the world of dust and fire. Personally, I always love seeing how something that looks so simple on the surface turns out to be incredibly complex inside. It reminds us that behind every ordinary thing, There's an entire army of people, machines, and scientific calculations. All right, I'm off to clean the dust off my camera, and you, don't forget to look at the world around you a little more carefully. See you at the next factory, where we'll definitely find something huge, loud, and absolutely fascinating. It's interesting that even in our age of digital technology and artificial intelligence, we're still dependent on a red-hot tube filled with limestone. You can write code for a new app, but you can't live in it. You'll still need a foundation, walls, and a roof. And that's exactly why cement plants aren't going anywhere. They're a reality you can't ignore. It's physics you can't hack. And that's what I love most about it. Here, everything is real. Touch this furnace, you'll get burned. Stand under that clinker stream, you'll get buried. No filters, no fakeness, just pure industrial power. We've traveled a lot of miles today, seen tons of raw materials and giant machinery, and every single time, I can't stop marveling at the scale. Humanity, this weird creature that decided caves weren't enough and started turning mountains into powder to build its own mountains out of glass and concrete. It's ambitious, it's bold, and it's very human. And you know what else is human? Subscribing to my channel right now. Alright, that's it. Tour's over for today. The air here's getting too thick, and my lungs are already begging for some clean forest air. But I'm sure tomorrow I'll want to come back to where the big machines work, because that's where you feel the real rhythm of our world. See you. Every year around the world, billions of tons of rock are blasted apart with explosives. Tunnels are carved straight through mountains, and rockets are launched into the sky. But few have ever seen the place where the force capable of reshaping landscapes in seconds is born. Today, we gained access to one of the most tightly guarded industrial facilities, where chemistry, fire, and metal come together to create the legendary TNT, the very substance whose explosive power became the world standard. But the scariest and most fascinating part isn't the explosion itself. It's how this yellow powder makes its journey from an ordinary liquid to a material that can obliterate a house-sized boulder. And trust me, if you stick around until the end, you'll learn a fact about TNT production that will completely change how you see modern industry. TNT, or trinitrotoluene as it's also called, showed up way back in the 18th century, when chemists started messing around with toluene. Americans call it TNT, short for trinitrotoluene, and to this day, it's the gold standard. 1 gram of TNT, the unit for measuring explosive force. Here at the plant, everything starts with massive tanks of toluene. This liquid flows into reactors, giant stainless steel vessels, where the temperature holds steady at 400 to 480 degrees Fahrenheit. No, seriously, it's hell in there. 200 to 250 degrees Celsius if you convert it. A mixture of nitric and sulfuric acids gets pumped inside. Concentrates so harsh, they'll melt your gloves right off. The nitration process runs anywhere from 3 hours to several days. First you get mononitrotoluene, then dinitrotoluene, and finally trinitro. The acids circulate in a closed loop. They get recycled instead of just dumping them into the ground. Operators in protective gear monitor the gauges, pressure, temperature, concentration. Everything's under control because the slightest shift and the reaction can go sideways. From the reactor, the mixture heads to coolers, long coiled tubes where the hot TNT crystallizes. Then settling tanks. The heavy TNT sinks to the bottom, while the lighter acids get drained off. That jelly-like mass right there, that's raw TNT, still wet with acid. They wash it with hot water at 150 to 180 degrees Fahrenheit to neutralize what's left. The water drains into the sewage system, and the crystals get dried in vacuum ovens, rotating drums that spin like washing machines. Massive stainless steel vats get pumped full of water at temperatures between 150 and 180 degrees Fahrenheit. The water jets out like in an industrial laundry, washing away residual nitric and sulfuric acid. TNT floats in it like jelly in boiling water, spinning, giving up impurities. The process takes half an hour. The water changes 3 times because the first batch is yellow from acid, the second is cloudy, and the third is already clear as a tear. This water doesn't just go down the drain. It gets neutralized with lime in basins, filtered through a 10-foot thick layer of sand, and then released into the river. Ecology stays under control because acid is poison for fish. Meanwhile, the crystals get unloaded. The mass becomes solid, but still 6 to 10% wet. Now comes the drying, the most interesting part. The entrance to this vacuum oven, a room where 20 rotary drums hum, each about 6 feet in diameter. TNT gets shoveled in there, 200 pounds at a time. The drum seals shut, air pumps out until pressure drops to 100 millimeters of mercury, and heating kicks in, 130 to 140 degrees Fahrenheit. Fans blast hot air through the center. The drum spins at 30 rotations per minute, like a washing machine on spin cycle. Crystals tumble, dry evenly, don't stick to the walls. 2 hours, and the doors swing open. Pure yellow powder, temperature 40 degrees, moisture content 0.5%. A worker in a mask pours it into hoppers, where a conveyor will carry it off to granulation. 5 tons per shift from one drum, and no dust because the vacuum pulls everything into filters. The operator jokes, "Dry as my sense of humor." Without this step, TNT would clump together or detonate from moisture. An hour or two, and we've got pure yellow powder. Color? Light yellow to dark orange, depends on purity. Here we get the top grade, 98% pure product. Next up, granulation. The powder gets moistened, pressed into briquettes the size of a matchbox, then crushed down to granules 2 or 5 thousandths of an inch in diameter. Why granules? Because the powder's easier to pack, doesn't create dust, and detonates evenly. I peer into the press, a giant machine with pistons pushing 200 atmospheres of pressure, and the briquettes come out hard as rock. Then the grinders, hammer mills where the shafts spin at 6,000 revolutions per minute. Dust gets vacuumed out by ventilation, because breathing in TNT, that's gonna cost you. Now packaging. Granules pour into airtight cardboard boxes weighing 100 pounds each. That's the standard for quarries and the military. Every box gets checked for moisture. No more than 0.70%, otherwise the TNT sweats and becomes sensitive. There are also barrel forms for underwater blasts. There the granules get mixed with paraffin so they don't get wet. Boxes are sealed, marked by lot, and done. Off to the warehouse. From here, TNT ships out to quarries, mines, defense. One box is enough to blast through 200 tons of rock. And then there's friction sensitivity. The cylinder spins for 6 hours, and if it doesn't blow, we're good. Lab techs in masks check purity with a chromatograph. Toluene or acid impurities aren't allowed. Nothing but respect. These people handle explosives like jewelers. Production is massive. 1,000 tons a month, that's millions of pounds. Energy? Electricity from gas turbines, steam from their own boilers. Waste? Acids get regenerated. Toluene gets redistilled. Environment? Filters on a 200-foot smokestack, wastewater treated until it's clear. Neighbors don't complain. The plant sits 10 miles from the nearest town. Fun fact, TNT doesn't just explode. They melt it at 82 degrees Celsius, 250 Fahrenheit, and pour it into shells like hot wax, or mix it with gunpowder for plastic charges. In quarries, 1 ton can shatter rock the size of a 3-story building. In mining, you can't punch through a mile-long tunnel without it. And in the military, it's the backbone of torpedoes, mines, bombs. You know how much steel came into this plant? Thousands of tons. Reactors made of chrome molybdenum steel, because regular steel just gets eaten alive by acids. I'm standing in the granulation shop right now. Hear that press rumbling? See those granules pouring into bins like golden sand? The air's clean, but it smells like nitrocellulose. Familiar scent if you've ever been to a powder plant. The operator laughs. Don't breathe too deep. or you'll detonate yourself. Joking, obviously. But the discipline? Ironclad. 8-hour shifts. Lunch break with the clatter of spoons on metal trays. Compare that to the old plants. Back then, everything by hand. Women in skirts packing TNT with bare hands. Explosions once a month. Now, robotic arms, sensors, cameras. Evolution. One worker monitors 10 processes from a control panel. And the pay? Competitive. The plant's like a living organism, roaring, churning, producing power. TNT isn't evil, it's a tool. Builds roads, digs mines, defends the country. Without it, no 1,000-foot bridges, no tunnels under mountains. Today, we're not at some sleek, modern factory. We're heading back in time, to an era when the entire world was engulfed in flames, and one nation that had peacefully built cars and refrigerators did something absolutely mind-blowing. This is the story of the arsenal of democracy, how American industry churned out so much weaponry in just a few years, it could have armed several planets. And we're looking at its crown jewel, the legendary flying fortress, the B-17 bomber. I spent weeks digging through archival blueprints, photographs, and records to tell you how a country that was making sedans for housewives yesterday started rolling out one bomber every single hour. So it's December 1941. Pearl Harbor's in flames, and America enters World War II. And the first question facing the government, where do we get planes? The B-17 bomber, developed by Boeing. It's an engineering marvel, but they're building barely any, almost one at a time. And the country doesn't need dozens, it needs tens of thousands of these machines. So President Roosevelt throws down the gauntlet to American industry, and that industry answers. And how it answers. Enter automotive giants like Ford and aircraft companies Douglas and Lockheed. They're told, guys, forget about cars. From now on, you build bombers. And that's when the real madness begins. Picture this. Ford, a company that had never built planes before, constructs from scratch in the middle of a Michigan cornfield, the world's largest factory at the time. Willow Run. This isn't just a factory, it's an entire city under one roof, a mile long. Over 40,000 people work here, many of them women coming into manufacturing for the first time. And they face a task that seems impossible. Put the production of a giant, complex bomber on an automotive assembly line. Nobody had ever done this before. You get why it was women, right? When America entered the war, millions of men, factory workers, farmers, mechanics, put on military uniforms and shipped out to the front. And suddenly, the factories that needed to produce tanks, ships, and planes sat empty. The country faced a massive labor shortage. So the government and industry turned to people they'd barely considered for heavy manufacturing before. Women. A powerful propaganda campaign rolled out. Famous posters showing a strong woman in a work bandana, flexing her bicep with the words, "We can do it," appeared across the country. And women answered the call. Millions of housewives, waitresses, secretaries, and recent high school graduates went to work in the factories. For them, this wasn't just a paycheck. It was patriotic duty, a way to do their part for victory, while their husbands, brothers, and sons fought thousands of miles from home. They proved they could do men's work just as well, sometimes better, becoming the unstoppable force that allowed American industry to work miracles. And here's where the American government and industry made some incredibly powerful moves. First, the government essentially forced Alcoa to share its technology and funded the construction of dozens of new, massive aluminum plants across the country. Entire cities were built, for example, in the industrial states of Washington and Tennessee. Why there? Because aluminum production is an insanely energy-intensive process. It relies on electrolysis from alumina, and that requires cheap electricity. And in these exact regions, the government had just finished building giant hydroelectric dams on the Columbia and Tennessee rivers. It was a perfect match. Huge amounts of clean, cheap energy waiting for someone to use it. Second, raw materials. The main raw material for aluminum is bauxite. Most of it had been imported from South America before the war. When the war started, German submarines began hunting merchant ships, and that route became dangerous. So America dramatically ramped up mining of its own bauxite, mainly in Arkansas, and secured the sea routes from the Caribbean as much as possible. But the most amazing part of this story is the grassroots movement. The government launched a massive patriotic campaign with the rallying cry, "Turn in aluminum for victory." School children, housewives, Boy Scouts, the entire nation started collecting aluminum scrap. People turned in old pots, pans, milk cans, parts from household appliances. It didn't have decisive economic significance, but it had a colossal psychological effect. Every American felt that their old pot could become part of a flying fortress wing that would fly off to strike the enemy. As a result of these titanic efforts, in just a few years, from 1940 to 1943, aluminum production in the US increased sixfold. The country didn't just cover its own needs, it started supplying this strategic metal to its allies. And that's how, through the combination of government will, industrial might, and the patriotism of ordinary people, America transformed a scarce pot metal into an endless stream of winged metal that became the lifeblood of its bomber armada. After stamping, each part needed 2 holes drilled on each side for rivets. And that's when the women stepped onto the stage. The legendary Rosie the Riveters. Thousands of young women who just yesterday were housewives or waitresses now stood at workstations, drilling these holes with incredible speed and precision. And then the real concert began. Thousands of pneumatic riveting hammers pounding aluminum simultaneously, creating a deafening non-stop roar. This was the sound of the arsenal of democracy being forged. Women worked in pairs. One held a massive bucking bar from the inside, while the other hammered the rivet from outside. Each rivet had to be perfect, because the aircraft's strength depended on it. And this is where Ford unveiled its main automotive trick, modular assembly. They didn't try to build the entire airplane in one place. Instead, they broke it down into large sections, or modules. In one shop, thousands of people assembled just the nose section of the fuselage. In another, just the center section with the bomb bay. In a third, gigantic wings, each over 50 feet long. Each section was assembled on its own mini assembly line, where it was packed with everything necessary. Miles of wiring were run, hydraulic lines installed, equipment mounts fitted. This allowed dozens of teams to work in parallel, without getting in each other's way. And then, these ready-made sections, packed with internal modules, looking like giant chunks of an aluminum construction set, got wheeled over to the main assembly line. This was the climax, a line a mile long. At the start, there's just the center wing section. Then 2 fuselage halves get joined to it. The whole structure moves freely forward. At the next station, they attach the nose and tail sections. Further down, they mount the massive wings. And so, step by step, right before your eyes, from separate pieces, a gigantic, nearly 100-foot aircraft takes shape. At the final stations, they install 4 powerful Wright Cyclone engines, each churning out 1,200 horsepower, mount the landing gear, glaze the cockpit, and of course, fit its main argument. 13 heavy-caliber Browning M2 machine guns, which gave it the name Flying Fortress. At peak production, in 1944, the Willow Run plant rolled out 1 B-17 bomber every 63 minutes. Just think about that. Every hour, 24 hours a day, a brand new, battle-ready heavy bomber rolled through those factory gates. It was a non-stop river of steel, aluminum, and firepower. In total, during the war years, 3 companies, Boeing, Douglas, and Ford, built over 12,700 flying fortresses. This wasn't just a victory of technology, this was a victory of logistics, organization, and most importantly, people. 1.5 million ordinary Americans who put aside their peacetime lives and became soldiers on the industrial front. They proved that a free nation, when united by a common paycheck, is capable of genuine miracles. That was the arsenal of democracy in action. Thanks for watching. Hit that like button, subscribe, and see you next time. Every year, humanity produces over 4 billion tons of concrete, more than any other material on the planet. It's what our cities, bridges, and roads are built from. But every crack is like a tiny timer ticking toward destruction, started the moment water seeps inside. Now imagine concrete that actually lives, breathes, and heals itself. No people, no repairs. Deep in labs across the Netherlands, USA, and Japan, a game-changing material is being born. Inside it, bacteria or microcapsules that can seal cracks on their own, just like skin healing after a wound. How is this even possible? How did a lifeless material gain the ability to regenerate? Stick around until the end, and you'll find out how scientists brought concrete to life. Self-healing concrete. Sounds like something out of a sci-fi movie, but it's already here. Scientists invented it to solve one of construction's biggest headaches: cracks. Regular concrete starts drying out and cracking over time from temperature swings, moisture, or just plain stress. And a crack isn't just a scratch. Water gets inside, the rebar starts rusting, the structure weakens, and eventually, you're looking at expensive repairs or even a collapse. That's why researchers decided to create concrete that can patch itself up, no human help required. Sounds crazy, but it's actually pretty logical. There are two main technologies that make this possible: microbiological and mineral. The first one uses real living organisms. So-called bioconcrete was developed by Dutch researchers, and the principle is pretty straightforward. They add special bacteria to regular concrete mix, usually Bacillus pseudofermis or Bacillus conii. These bacteria can stay dormant for years, like seeds in dry soil. Along with the bacteria, they add nutrients, usually calcium lactate. And while the concrete stays intact, the bacteria just sleep. But when a crack forms and moisture gets in, they wake up. That's when the real microscopic work begins. The bacteria start consuming the nutrient substrate and, through their life processes, produce calcium carbonate, basically the same mineral that makes up seashells and limestone. That's what seals the crack from the inside, like the concrete is fixing itself. The results are impressive. Micro cracks up to 0.03 of an inch can disappear completely within a few weeks. And all without human intervention, purely thanks to nature that's been built into an artificial material. The second technology is less alive, but no less impressive. Instead of bacteria, it uses chemistry. Tiny capsules are added to the concrete, containing an active substance inside. For example, epoxy resin or sodium silicate. These grain-sized capsules are evenly distributed throughout the mix. When the concrete cracks, some of the capsules burst too. The substance inside comes out, fills the crack, and hardens on contact with air or moisture. The result is the material literally heals itself. It's similar to how certain car paints can heal scratches with heat, except this process is way more complex and large-scale. The advantage of this approach is that it works even in dry conditions, where bacteria might not activate. The downside is cost. Creating the capsules is more complex, so this concrete is pricier. But when you calculate the cost of repairing bridges or tunnels, it becomes clear. The payoff is huge. Interestingly, these technologies don't cancel each other out. Some companies are experimenting with combining biological and chemical methods to create concrete that could self-heal under any conditions. Underwater, in the desert, or in freezing cold. Testing shows that structures made with this concrete last 2 to 3 times longer than regular ones. Bridges, roads, dams, parking garages, all of this can be made nearly eternal. For example, The Netherlands already built a lakeside lifeguard station using bioconcrete, and after several years, it hasn't needed any repairs. The idea is spreading fast around the world. In the US, these materials are being tested in bridges, in the UK, in sidewalk paving, and in Japan, even in concrete for coastal reinforcements that have to withstand salt water. Regular concrete, even the highest quality, has a shelf life, roughly 50 years. After that, cracks start appearing, water penetrates inside, rebar rusts, and the structure gradually weakens. Self-healing concrete changes these rules. Thanks to bacteria or microcapsules, it can heal microdamage before it becomes a problem. That's why the service life of structures can nearly double, from 100 to 120 years. That means one bridge or building can stand for 2 human generations without major repairs. Sure, this material isn't cheap yet. It costs several times more than regular concrete, on average 3 to 5 times more. But if you look at the long game, it's totally worth it. Maintaining, repairing, and restoring structures costs governments and companies millions of dollars every year. Self-healing concrete cuts those costs to a minimum. Basically, it's like buying a car that changes its own oil and fixes its own brakes. Expensive up front, but then smooth sailing and economical. The Netherlands became the real home of self-healing concrete. Right here, at Delft University of Technology, the idea emerged to add living bacteria to the mix that could repair concrete from the inside. The man behind this idea is Dutch microbiologist and engineer Hendrik Jonkers. Nature inspired him. He noticed that certain bacteria can survive in limestone rock and create mineral deposits, filling micro cracks in stone. That's when Jonkers asked himself, if nature can heal stone, why not make concrete that does the same? In the early 2000s, he started experiments with different bacterial strains, looking for ones that could withstand concrete's alkaline environment and stay viable for years. After numerous trials, the best candidates turned out to be Bacillus pseudofirmis and Bacillus conii, spores that can sleep for decades and activate only when moisture appears. Jonkers added them to concrete along with a food source, calcium lactate. The results were mind-blowing. When the concrete cracked, the bacteria woke up and produced calcium carbonate, which sealed the cracks like natural glue. Jonkers called his invention bioconcrete, and soon the whole world was talking about it. Later, Delft University launched a project to test bioconcrete under real-world conditions. In 2015, the Netherlands built the first lakeside structure using this material. Years later, it remained in excellent condition without any repairs. Now Jonkers' lab is working with construction companies and governments from other countries, perfecting the formula to make it cheaper and more accessible. The USA and UK bet on the mineral technology for self-healing concrete, which doesn't require living organisms, but works through special microcapsules with healing substances inside. These countries are actively investing in research on materials that can automatically restore minor damage without human involvement. The principle is pretty simple, but looks impressive. Capsules or microcapsules filled with special gel, epoxy resin, or sodium silicate are added to the concrete mix. When the concrete surface stays intact, the capsules preserve their contents without reacting with the environment. But as soon as a crack appears, the capsule ruptures and the liquid flows into the damaged zone. On contact with moisture or oxygen, the substance hardens, gluing the crack edges together and returning the structure's original strength. These systems are currently being tested in US Army labs and British research centers, including Cambridge University. In the UK, they're even building experimental road and bridge sections with this material to track how it behaves under rain, vibrations, and temperature swings. American experts went even further. They're experimenting with capsules that can activate multiple times. Inside these capsules are microgels that not only fill cracks, but also expand on contact with water, creating a hermetic barrier against corrosion. This is especially crucial for bridges and skyscrapers in coastal cities, where concrete constantly faces moisture and salts. test results show that cracks up to a few hundredths of an inch wide can seal themselves in less than a week. And if the damage is larger, the process takes longer, but still happens without human involvement. Such technologies can significantly extend the service life of roads, tunnels, and even military structures, which is especially valuable under extreme loads. Thousands of planes, just sitting in the desert. They'll never fly again. But each one? Millions of dollars being carefully stripped away, bolt by bolt, right now. One engine, 30 million. Business class seats, a few thousand each. Even the coffee maker from an old Boeing gets auctioned off. People think aircraft boneyards are graveyards. But the truth is, they're the most profitable recycling operations on the planet. Today, we're going where almost no one gets to go. To watch a 150-ton giant get torn down to scrap metal in 30 minutes. And why this isn't the end at all. It's a whole new beginning. Why the desert? That's the first question that pops up when you see these thousands of acres packed with plains. It's pushing 100 degrees Fahrenheit out here, and the humidity's basically zero. Perfect conditions to keep metal from rotting and rusting. Planes can sit here for decades and still look like they rolled off the tarmac at JFK yesterday. But not all of them are here to die. A lot are just waiting for better times. The airplane recycling process starts with what the pros call harvesting. This is the most profitable part of the job. When an airline decides a plane is no longer flight-worthy, engines are the first things to go. One of those engines can run anywhere from $10 to $30 million in working condition. They're pulled using special lifts and shipped off for diagnostics. Even if the airframe itself is old, those engines can keep flying on other aircraft for years to come. It's like a heart that keeps beating in another body. Besides the engines, they remove the auxiliary power unit. That's a small engine in the tail of the plane that provides electricity when the main motors are shut down. That thing's worth serious money too. Next, we step inside the cockpit. For aviation fans, this is like Aladdin's cave. There are hundreds of switches, screens, and computers. Each black box or navigation instrument can fetch several thousand or even tens of thousands of dollars on the secondary market. Workers remove all the equipment very carefully, pack it into special anti-static boxes, and send it for testing. Same goes for the passenger cabin. You'd be surprised, but even the seats have value. A set of business class seats can be sold for several $1,000s to private companies or movie studios building sets. Galleys, meal carts, even coffee makers, everything goes up for sale. There's nothing worthless on a plane until it's just an empty metal tube. Once everything valuable is stripped out, the environmental specialists step in. An aircraft is a complex machine packed with hazardous fluids. Every last drop has to be drained. The fuel tanks of a large plane can still hold several hundred gallons of kerosene that can't be pumped out during normal operations. Hydraulic fluid also needs draining. It's highly toxic, along with lubricant from all the mechanisms and antifreeze. Just imagine, the total volume of all these technical fluids can reach 500 gallons. All of it gets drained into special tanks for proper disposal. Workers also remove batteries, fire extinguishers, and oxygen cylinders. If even one of those cylinders stays inside when the heavy machinery moves in, it can explode with the force of an artillery shell. When the plane becomes completely clean, the most spectacular part begins, destroying the fuselage. Here we see a giant excavator at work, but instead of a bucket, it's equipped with hydraulic shears. They're sometimes called the guillotine. The operator of this machine is a true master. He drives up to the aircraft and starts chomping off pieces of the wings. The sound is like someone tearing open a giant soda can, only 1,000,000 times louder. The metal crunches, cracks, and gives way under pressure of several thousand pounds per square inch. First they cut off the wings, then the tail section. All of this is done according to a specific plan, so the structure doesn't collapse onto the machine itself. Next, the excavator tackles the fuselage. It simply slices this massive steel tube into chunks about 20 feet long. This is done so these pieces can be loaded onto regular trucks and hauled to the metal mill. Watching what was once a majestic airliner that flew at 30,000 feet get turned into a heap of mangled metal in 30 minutes. It's a sight that makes you think about how fleeting time really is. But the equipment operators don't have time for philosophy. They need to sort the scrap as fast as possible. Sorting is the key to profit in this business. An aircraft is made up of different metals, and they can't be mixed. About 80% of the weight is aluminum, but it also comes in different grades. The skin is one alloy. The structural beams inside are another. There's also titanium, which is used in high temperature areas, like near the engines. Titanium costs several times more than aluminum, so there's a real hunt for every piece of this metal. There's also steel in the landing gear, and some copper in those leftover wires that couldn't be pulled out by hand. Workers use magnets and special scanners to separate these piles of metal. A lot of people think aircraft scrap is the end of the story, but it's actually the beginning. The aluminum from these planes, it's the highest quality metal. They melt it down at around 1200 degrees Fahrenheit and make new ingots. From that aluminum, they can then make just about anything. Beer cans, parts for new cars, or even new aircraft. It's a closed loop where nothing goes to waste. Experts say roughly 95% of a modern passenger jet's weight can be recycled and used again. That's an incredible number for such complex machinery. Here's a fun fact for those who love numbers. In 1 year at a boneyard like this, they can completely dismantle up to 200 aircraft. If you take the average weight of each at 150,000 pounds, that's 30 million pounds of metal going back into the economy. This is a billion-dollar business, and it's only growing because airlines are trying to upgrade their fleets faster to more fuel-efficient models. Older planes become too expensive to maintain, so they end up right here, under the Arizona sun. There's always something a little sad about watching planes die. But at the same time, I'm blown away by how incredibly organized this whole process is. There's no chaos here. Every swing of the excavator, every step a worker takes with a wrench in hand, it's all calculated down to the second. This is a massive machine that converts the past into the future. We've just watched hydraulic power transform a symbol of technological progress into raw material for new achievements. And even though these aircraft will never take to the skies again, they live on in the things we use every day. As we walk across this yard, there's a constant crunch of broken glass and insulation debris under our feet. The air smells like hot metal and dry grass. It's a unique atmosphere that's tough to capture in words. This is where engineering genius meets inevitable destruction. But it's not destruction for destruction's sake. It's destruction for the sake of creating something new. And that's really what our civilization is all about. We're constantly recycling the old to build something better, faster, and more efficient. I hope you enjoyed peeking behind the fence of this aircraft graveyard with me. Now, next time you're flying off on vacation, you'll know what awaits your plane in 20 or 30 years. And it's not scary at all. It's just another chapter in the life of metal and technology. Thanks for watching my explorations. Hit that like button if you're into massive machinery like this, and subscribe so you don't miss new journeys to the most fascinating places on our planet. We'll find plenty more spots where metal tells us its incredible stories. See you in the next video, where we'll tear apart something just as epic. Bye. Every year, machines are built around the world so massive and powerful that a single one could supply electricity to an entire city, and costs as much as dozens of private jets. But what if I told you that inside this colossal structure, there are parts machined with precision, thinner than a human hair, and that one tiny mistake could cost millions of dollars or even destroy everything? Today we're going inside a place almost no one gets to see, the heart of turbine manufacturing. And trust me, what you're about to see will completely change how you think about engineering, if you stick around till the end. Let's start with the fact that there are two main types of these turbines, and they work on very different principles. First, the steam turbine. You'll find these at nuclear and thermal power plants, on massive tankers and icebreakers. Second, the gas turbine. It's more like a giant jet engine without wings, and lives mostly at gas-fired power plants and on some military vessels. Here at the factory they make both types, but we're heading first to the steam ones, because they're older, more massive, and look like they were invented 2 centuries ago. Which, actually, they were, but they're still very much around. How a steam turbine works: short and formula-free. There's a boiler that heats water into pressurized steam at anywhere from 800 to 3,000 pounds per square inch. This steam, hot, pressurized, angry, blasts through nozzles onto rotor blades. The blades start spinning. The rotor spins the shaft. The shaft spins a generator or a ship's propeller. The steam cools down, condenses back into water, and returns to the boiler. The cycle is closed. Sounds simple, but for this simple not to explode into pieces and to run for 3 years without major repairs, you need all of this around me. The first shop they take me to is the foundry. This is where every turbine begins. The casing, the outer shell that holds all the internal components under pressure, is cast from alloy steel or cast iron, depending on operating parameters. For steam turbines in large power plants, the casing is cast in 2 or 3 tiers, and each tier is a separate mold. The mass of 1/2 of a casing can reach 60 to 80 tons. The metal is melted in arc furnaces with a capacity of 50 to 150 tons of molten metal, and the temperature there is around 5,000 degrees Fahrenheit. The mold for a large casing is a pit in the floor, 6 to 10 feet deep, lined with refractory clay. The metal is poured through a system of channels, and the entire process of filling one large mold takes 15 to 30 minutes. Then the casting cools, naturally from several days to 2 weeks, depending on the mass. After cooling, the casting goes to its first inspection. Ultrasonic testing searches for voids and inclusions inside, spots where the metal didn't fuse the way it should. X-rays check critical zones. If they find something significant, the casting goes back to remelt. No compromises. The rejection rate at this stage runs 3 to 8% depending on the casting's complexity, and that's completely normal for parts this size. Next, machining. Now, here in the shop floor, there are machines that made my jaw drop. The horizontal boring mill that machines the inner casing surface. It's about 60 feet long. The table where the part sits moves. The spindle stays put. The tool freely bores the bearing and seal mounting surfaces to an accuracy of plus or minus 0.5 of an inch. Why so precise? Because the rotor spinning inside at 1500 to 3600 revolutions per minute has a clearance between its blades and the casing of 50 to 150 microinches. 1% efficiency loss at a large power plant. That's millions of dollars in extra fuel costs per year. The rotor is the star of this story. It's a shaft carrying discs with blades, and it's the most complex part of the entire turbine. The shaft for a large steam turbine is a forging made from special chromium molybdenum vanadium steel, 20 to 40 feet long and weighing 20 to 60 tons in its rough state. A forging means you take a red-hot ingot of metal and just hammer it with a press weighing 5,000 to 50,000 tons to give it the shape you need. The grain structure of the metal during forging gets oriented along the shaft's axis. That's how you achieve torsional strength. After forging, the shaft goes through heat treatment again, then heads to the machine shop. Turning takes 2 to 4 weeks of continuous work on a lathe that's nearly 70 feet long. Chips fly, coolant flows, and machining away from that massive blank reveals the sleek shaft you saw in the drawings. This is the part where I'm always amazed. A gigantic component, yet precision like a watch mechanism. Blades are a separate production line. Steam turbines at large power plants have anywhere from 8 to 20 stages, and each stage is a disc with blades. First stage blades are small, sometimes less than 2 inches tall, because the steam there is still under high pressure and dense. Last stage blades are massive, up to 5 or 6 feet long on the largest turbines. These blades are forged and milled from iron-based alloys or stainless steel, and in their final profile, they have an aerodynamic shape with precision to within plus or minus 0.002 of an inch along the entire length. Each blade is checked for resonant frequency. It can't match the operating rotational frequency of the rotor, or else after a few thousand hours, a fatigue crack will develop from vibration. How they test this is simple. They tap the blade with a small hammer and listen with a special acoustic sensor. A very elegant method for such a serious problem. Assembling the rotor. This is when it starts to feel like an operating room. Bladed discs get mounted onto the shaft using shrink fitting. The disc gets heated to 300 to 400 degrees Fahrenheit. It expands, slides onto the shaft, then cools and grips the shaft with a force no bolt could ever match. No threads, no glue, just temperature difference and precision sizing. The interference fit when cold, 1 to 3/1000 of an inch per inch of diameter. After assembly, the rotor gets balanced, and this takes 1 to 3 days. Balancing happens on a specialized rig, where the shaft spins on bearings while sensors register vibration. If there's any imbalance, metal gets removed from certain spots, or balancing inserts get installed. Allowable residual vibration on a large rotor, fractions of an ounce per inch of radius. If you think that's strict, you're thinking right. After assembly, the turbine heads to the test stand. At full operating parameters, pressure and temperature, they run the turbine for 24 to 72 hours. Sensors track bearing temperatures, vibration, steam leaks, power output. If anything goes outside the limits, stop, disassemble, analyze. There have been cases where they found a defect here that the X-ray missed initially. So the test stand isn't just a formality. It's the last line of defense before shipping. The finished turbine gets broken down into transport blocks, casing separate, rotor separate, auxiliary equipment separate. A large turbine rotor travels on a special trailer with hydraulic suspension, the kind you've seen on YouTube, with 18 axles moving at 20 miles per year. They coordinate the route a month in advance. Every bridge height and every turn width needs checking from the factory to the port or customer. Sometimes for one of these transports, they temporarily remove road signs and even take down power lines over the highway. I asked the chief engineer how many turbines they build per year. He said 12 to 20 of various types. That's it. Less than 2 per month. But each one runs for 30 to 50 years and generates electricity for hundreds of thousands of people every day. Some things don't need high-volume production. What if I told you that a high-speed train wheel experiences temperatures hot enough to make metal glow, and still can't afford to fail? Why must this piece of steel withstand tests that would destroy any car wheel in seconds? There's a reason almost nobody suspects, and if you stay with me through to the finale, you'll discover the secret process that forces the wheel to survive where other metal simply melts. But first, tell me, does your country actually manufacture railway wheels? Or are they imported? A train rockets down the tracks at over 186 miles per hour. At that speed, an ordinary wheel would simply disintegrate. Why? Because it has to withstand not just weight, but a whole series of inhuman trials. The material is everything. This isn't ordinary steel used for silverware or even car bodies. High-speed train wheels are made from a special grade of steel, melted according to a unique, meticulously refined recipe. This recipe is a combination of iron with specific alloying elements, manganese, silicon, chromium, molybdenum, that give the steel extraordinary strength, toughness, the ability to absorb impacts without failing, and endurance. Beyond that, this steel must be as pure as possible, free of any foreign impurities that could become a weak point. After the special steel is melted in massive metallurgical furnaces, it's poured into molds to create large steel billets, what we call slabs or blooms. But that's just the beginning. The real transformation starts in the forging shop. This is where one of the most powerful forging presses comes into play, along with specialized forging machines. The billet, heated until it glows bright yellow or red, that's around 2000 degrees Fahrenheit, is fed under the press. The process involves multi-stage forging. It's not a single strike, but rather a whole series of controlled pressures and rotations. The giant hammers, or jaws of the press, slowly, yet with unstoppable force, flatten and shape the red-hot metal. First stage, the billet is compressed to give it a rough circular shape, densifying the metal and eliminating internal voids. Second stage, the material is flattened and rolled, forming a disc with a central hole. This is where the future wheel's outline begins to emerge, with its rim, disc, and hub. This directional metal flow shapes its internal fibrous structure, making the wheel exceptionally strong in the required directions. Forging, unlike casting, transforms steel's microstructure. It compresses the metal's grains, eliminates casting defects, and creates a directional fibrous structure that gives the wheel exceptional strength and fatigue resistance. It's like an athlete's muscles. After training, they become stronger and more resilient. Why such complexity? Because high-speed train wheels operate under extreme conditions that are hard to imagine. When moving at speeds over 186 miles per hour, the wheel's surface heats up from friction against the rails and brake pads to nearly 2000 degrees Fahrenheit. That's the temperature at which metal begins to glow red and change its properties. And this heating isn't constant, it's cyclical. Heating during acceleration and braking, cooling during movement. The material must withstand these constant temperature fluctuations without forming microcracks, which over time can lead to failure. Each pair of wheels carries a load of dozens of tons. A single railcar can weigh between 50 and 70 tons, and this weight is distributed across just 4 wheels, that is, 2 wheel sets. This creates constant pressure acting on the wheel. The train doesn't ride on a perfectly smooth surface. It crosses rail joints, uneven sections, and switches, which generate continuous impact loads. The wheel must be incredibly tough to absorb these shocks without cracking or breaking apart. After forging, the wheels aren't finished yet. They undergo complex heat treatment, which is key to developing their final properties. The wheel centers, the discs that connect the hub to the rim, are hardened. Hardening is a process of heating steel to high temperatures, then rapidly cooling it. This makes the metal harder and stronger. But hardening makes the metal brittle, so it's always followed by tempering, reheating to a lower temperature with slow cooling. Tempering reduces brittleness and improves toughness while maintaining high strength. This combination of hardening and tempering creates the ideal steel microstructure that can withstand extreme operating conditions. But even after all these complex processes, no wheel reaches the rails without brutal yet necessary testing. Every single wheel, without exception, undergoes ruthless inspections. Ultrasonic testing. It's like medical ultrasound diagnostics, but for metal. Special sensors send high-frequency ultrasonic waves through the wheel. If there's even a microscopic crack, void, or defect inside, the ultrasonic wave bounces off it and creates an echo that the instrument captures. This method allows us to see internal defects without destroying the wheels. A defect the thickness of a human hair is already grounds for rejection. Magnetic particle inspection. The wheel gets magnetized, then its surface is coated with fine ferromagnetic powder. If there's a crack, even one invisible to the naked eye, it distorts the magnetic field, and the powder concentrates along that crack, making it visible. This reveals even the tiniest surface defects that could become failure points during operation. Only wheels with perfect structure and 0 defects are cleared for installation on high-speed trains. This isn't engineering perfectionism. It's about the safety of thousands of passengers who trust their lives to these metal giants. While the United States isn't leading high-speed rail development like China or Japan, its rail network remains one of the world's largest, and American manufacturers have extensive experience producing high-quality wheels for various rolling stock, passenger trains, freight locomotives, and switching equipment alike. Unlike the automotive industry, where thousands of companies manufacture parts, the railroad wheel manufacturing market in the US is significantly more concentrated. This is a highly specialized field, requiring massive investments in metallurgical equipment, forging presses, and quality control systems. The two main and most powerful players in the North American railroad wheel manufacturing market are Amstead Rail and KF USA. While KF is a Spanish company, it maintains production facilities in the United States to meet local demand. Previously, other major manufacturers existed, but the market has consolidated. Total annual railroad wheel production in the US fluctuates, but can be estimated in the range of 300,000 to 500,000 units per year. This figure includes wheels for all types of rolling stock. It's worth noting that while the US can manufacture wheels capable of withstanding high speeds, the actual demand for wheels designed for continuous operation above 186 miles per hour remains relatively limited due to the scarce number of true high-speed rail lines in the country. For instance, Amtrak's Acela Express trains, running along the Northeast Corridor, reach speeds up to 150 miles per hour on certain segments, but not beyond the aforementioned threshold of 186 miles per hour, which requires specific material and design standards. However, US wheel manufacturing technologies and standards do enable production that meets international requirements for high-speed trains should the need arise. From a material standpoint, American manufacturers, like their global counterparts, utilize specialized grades of carbon steel alloyed with manganese, silicon, and other elements to achieve the necessary strength, wear resistance, and toughness. Forging, heat treatment, and non-destructive testing processes are standard and comply with the highest international safety and quality benchmarks. Every 3 seconds worldwide, a new engine block rolls off the production line, the heart of a car that will withstand millions of explosions, temperatures over 4,600 degrees, and operate for decades without stopping. But how do you transform molten metal into a perfect mechanism with precision down to a micron? One mistaken dimension, and the engine will tear itself apart within minutes of operation. Every year, over 100 million of these blocks are manufactured, and each one goes through a hellish birthing process. Molten metal at 5,400 degrees, sand molds that self-destruct, and robots that cut channels thinner than a human hair. But there's one secret the manufacturers don't talk about. A mystery hidden inside every block that determines whether your car will go 60,000 miles or 600,000. Stay until the end. What you'll learn will forever change how you see what's happening under your car's hood. Let's start by understanding what an engine block actually is. It's the foundation that holds the entire engine together. Inside it are the cylinders where fuel combustion occurs, pistons that move up and down, and other critical components. The engine block must be strong, lightweight, and resistant to high temperatures. That's why manufacturing it is a complex process that demands precision and advanced technology. Everything begins with an idea. Engineers develop a concept for an engine that must be powerful, economical, and environmentally friendly. They use specialized 3D modeling software to create a digital model of the block. This allows them to account for every detail and test how the engine will perform under various conditions. Engine blocks are made from different materials, but the most common are cast iron and aluminum. Cast iron is strong and resistant to high temperatures, but heavy. Aluminum is lighter and dissipates heat better, but less durable. Sometimes composite materials or alloys are used to combine the advantages of both metals. After the engineering team completes all calculations, computer modeling, and finally approves the design of the new engine block, the true heart of the future automobile, the most interesting part begins: its birth in metal. The first and perhaps oldest step in metallurgy is casting. A massive shop filled with the hum of machinery, the smell of molten metal, and the glow of high temperatures. This is the foundry, where engineers' dreams become real components. First, a mold for the block is created. There are two main approaches to creating these molds, each with its own advantages. The first, and most common for large-scale production, uses sand molds. This is an amazing, though traditional method. First, they make a pattern of the future engine block, usually manufactured from wood or metal, and it's an exact copy of the block, but accounting for certain features, such as compensation for metal shrinkage during cooling. Then this pattern is placed in a special container, where it's tightly packed with a mixture of quartz, sand, clay, and organic binding agents. This mixture is compacted, then baked or chemically hardened, creating a strong but porous mold. After this, the pattern is carefully removed, leaving a cavity that precisely matches the shape of the future block. The most challenging aspect of sand molds is creating internal cavities, coolant channels, oil passages, cylinder bores. For this, they use so-called cores, separate elements, also made from sand, that are inserted into the mold. After pouring the metal and cooling, the sand is easily removed, leaving the necessary internal channels. The advantage of sand molds is their relative affordability per unit at large volumes and the ability to create very complex internal geometries. The second method, often used for aluminum blocks or smaller production runs, uses metal molds or permanent molds. These are stronger, reusable molds made from steel or cast iron. They're more durable and allow for parts with smoother surfaces and higher dimensional accuracy right from the casting stage. However, metal molds are much more expensive to manufacture, and it's harder to adapt them for creating the very complex internal channels found in engine blocks. Therefore, they're often combined with sand cores for internal cavities. The chosen material, cast iron or aluminum, is melted in a furnace at high temperature. For cast iron, this is typically over 4,600 degrees Fahrenheit. For aluminum, around 3,000 degrees. In massive induction or arc furnaces, metal scrap and pure ingots slowly transform into a glowing, liquid mass that shines bright orange or silvery light. This process includes precise control of chemical composition. Metallurgists add special alloying elements, such as silicon, magnesium, copper, in strict accordance with the recipe, to give the future block necessary properties: strength, wear resistance, lightness. The molten metal is constantly stirred and goes through refining processes to remove unwanted impurities that could reduce the quality of the finished part. Finally, the climax arrives: pouring. The molten metal, radiating intense heat, is carefully transferred from the furnace into special ladles, then into the prepared molds. This is the moment of maximum concentration and precision. The metal must fill every cavity of the mold, displacing air and completely matching its configuration. The pouring process can be gravitational, meaning the metal simply flows under gravity or under pressure, which ensures better mold filling and reduces porosity. After pouring, the mold remains for some time, so the metal can cool and solidify. This can take from several minutes to several hours, depending on the block size and metal type. When the metal has cooled and fully crystallized, the next stage occurs. The mold is broken apart. If it's a sand mold, it's simply destroyed using vibration or hydraulic hammers, freeing the newly created metal object. The sand is later collected and partially recycled. If it's a metal mold, it's opened, and the finished block is carefully extracted. As a result of this process, we get what's called a rough engine block. It's not perfect yet. Its surface is rough, it may have sand residue or so-called flash, small metal overflows at the mold seams. It doesn't yet have mounting holes, and it lacks the micron tolerances required for engine operation. But it's already a real block, massive and heavy if it's cast iron, or surprisingly light if aluminum, but already with a clearly defined shape, ready for the next processing stages that will transform it into a high-precision part capable of withstanding incredible loads inside the engine. Mechanical processing is performed on specialized computer numerically controlled machines. The large, solid block is secured on a special table. Around it, various tools move, performing their work. Like a scene from some movie, isn't it? Let's start with the most obvious, cylinder bores. These holes must be perfectly round, have precise diameter, and be positioned exactly on one axis, since pistons will move within them. First, machines use large end mills to roughly remove material, creating preliminary holes. It's like carving out a large chunk from cheese. Then more precise tools come into play. Special boring cutters are used, which carefully remove the thinnest layers of metal, bringing cylinder diameters to the required size. This happens in stages, with constant dimension control. After this, cylinder walls undergo honing. This is final abrasive processing that creates very fine, cross-hatched scratches on the internal surface. These scratches retain lubricant, ensuring perfect lubrication of piston rings and minimizing friction, which is critically important for engine efficiency and longevity. Actually, the cylinder surface after this processing feels perfectly smooth to the touch, but under a microscope has the perfect structure for retaining an oil film. Next, oil and cooling channels. These systems that penetrate the entire block are vitally important. Oil channels deliver lubricant to all moving engine parts, such as the crankshaft, camshaft, pistons, ensuring their lubrication and heat removal. Cooling channels circulate coolant, removing excess heat generated during fuel combustion and maintaining optimal engine operating temperature. The internal, complex labyrinths of coolant and oil channels, as we mentioned, are formed during the casting stage using sand cores. But after this, they need to be opened and brought to perfect condition. For this, high-precision drills and mills are used to create inlet and outlet openings for these channels, and also connect them with other engine parts. Each hole must be positioned with millimeter, or even micron precision, so fluids can circulate freely. Your house has no electricity. Your phone doesn't exist. The internet is physically impossible. Electric motors of any kind can't be built. And human civilization is frozen in the 1800s with steam engines and gas lamps. All because we never figured out how to refine one reddish metal that conducts electricity better than anything else except silver, which costs 50 times more. Without this metal, every wire would need to be 3 times thicker and cost 4 times as much. Power grids couldn't reach beyond cities. Your electric bill would be $1,200 monthly. Today, we're going inside the factory in Utah, where this metal gets refined to 99.99% purity, and I'll show you why that purity matters, and what would happen if we used something else instead. The Kennecott Copper Refinery in Magna, Utah, sits 12 miles west of Salt Lake City, and has processed copper continuously since 1903. This facility receives ore from Bingham Canyon Mine 20 miles south, the largest man-made excavation on Earth visible from space. The refinery processes 300,000 tons of copper per year, and every step creates properties that make electrical civilization possible. Raw copper ore contains only 0.6% actual copper mixed with rock and minerals. If copper was never discovered, we'd use aluminum for electrical wiring. Aluminum conducts only 60% as well as copper, meaning you need 50% more cross-sectional area for the same current. Every wire in your house would be thicker and heavier. Building construction costs would increase 30% just from wiring. The first stage crushes ore into powder and mixes it with water and chemicals in flotation tanks. Air bubbles blow through, and copper minerals stick to bubbles and float as froth while waste rock sinks. The froth contains 30% copper, a 50-fold increase from raw ore. This concentration matters because copper's conductivity depends entirely on purity. Even tiny impurities dramatically increase resistance. 1% phosphorus increases resistance by 50%. 0.1% arsenic doubles it. Without purification, we'd use metals that lose huge amounts of energy as heat. Power companies would generate 3 times more electricity just to compensate for transmission losses, 3 times more power plants, fuel, and pollution. Concentrated ore moves to the smelter and heats to 2,200 degrees Fahrenheit. Copper melts and separates from sulfur and iron, which becomes slag. What emerges is blister copper at 98% purity. Better, but not good enough for electrical use. Copper's heat tolerance becomes important here. It carries high currents without melting, doesn't melt until 1984 degrees Fahrenheit. Aluminum melts at only 1221 degrees. In electric vehicle motors or transformers, aluminum would literally melt under load. Electric motors would need to be 3 times larger to keep current densities low enough. A 200-pound copper motor would weigh 600 pounds in aluminum and deliver less power. Blister copper moves to electrolytic refining, the most critical stage. Impure copper sheets become anodes in giant tanks with acidic copper sulfate solution. Pure copper cathodes sit opposite, and when current passes through, pure copper ions migrate to cathodes while impurities fall to the bottom. After 12 days, cathodes are coated with 99.99% pure copper. This extreme purity creates extreme conductivity. At 99.99%, copper conducts so efficiently that a mile-long wire loses only 2% power as heat. At 98% pure, that wire loses 15%. With aluminum at any purity, you lose 5 to 8%. The United States has over 600,000 miles of high-voltage transmission lines. If those were aluminum instead of copper, we'd lose 200 billion kilowatt-hours per year in transmission, enough to power 20 million homes. Your electric bill would triple. Pure copper cathodes get melted and cast into forms. Some become wire rod drawn through progressively smaller dies, creating wire from thick power cables to hair-thin magnet wire. Others get rolled into sheets for circuit boards and building materials. Each application requires different properties, but all depend on 99.99% purity. Copper's combination of conductivity and ductility becomes critical here. Copper can be drawn into micron-thick wire without breaking. Aluminum is brittle. When you bend aluminum wire repeatedly, it cracks. This is why every electric motor uses copper windings. The wire bends around tight curves hundreds of times during manufacturing without breaking. Without copper, we couldn't mass-produce electric motors. No motors means no electric vehicles, power tools, washing machines, fans, or pumps. Every copper batch goes through rigorous testing, and there's a specific reason purity standards are so strict. During the 1960s and early 70s, copper prices spiked, and builders used aluminum wiring in homes to save money. Aluminum was cheaper, but had higher resistance, running hotter under load. The real problem was connections. Aluminum expands and contracts more than copper when heating and cooling. Over months of electrical cycling, aluminum wire worked loose from connection points. Loose connections create more resistance and heat. The insulation would char and ignite. Between 1965 and 1973, tens of thousands of house fires traced back to aluminum wiring. Dozens died. Insurance companies refused to cover homes with aluminum wiring. That crisis proved copper can't be substituted. Today, every copper product goes through conductivity testing. Pure copper at 20 degrees Celsius has conductivity of 58 million Siemens per meter. Anything below 57 million gets rejected and reprocessed. They also do bend testing, thermal cycling, and microscopic inspection. The rejection rate is 6%. Copper that passes inspection ships to manufacturers making electrical wire, motors, and electronics. Kennecott produces 300,000 tons yearly, but global production is 25 million tons because demand is enormous. Without copper, no electrical grid exists as we know it. Thomas Edison tried iron wire for electrical distribution in the late 1800s. It didn't work. Resistance was so high that power couldn't travel more than a few blocks. Without copper, electrical power is limited to buildings with their own generators. No power lines between cities. Every building needs its own coal or diesel generator running constantly. The internet is physically impossible. Fiber optics carry data long distances, but electronics at each end require copper for power and short-range transmission. Data centers use thousands of miles of copper cabling. Without copper, you might have mechanical telegrams, but no electronics, computers, or digital communication. Electric motors don't exist in practical form. Every motor requires copper windings for electromagnetic fields. Aluminum motors are 3 times larger for the same power, overheat easily, and fail quickly. Without copper motors, manufacturing never industrialized beyond steam power. Modern factories don't exist. Every product is more expensive because it's made by hand. Transportation is completely different. No electric trains. You're stuck with diesel locomotives. No electric cars. Tesla doesn't exist because you'd need a 6,000-pound aluminum motor to move a 2,000-pound car. Ships use massive diesel engines instead of efficient electric systems. You've seen how copper ore concentrates from 0.6% to 30% through flotation, how 2,200-degree smelting separates copper from impurities, how electrolytic refining creates 99.99% purity, making efficient electrical transmission possible, and why the aluminum wiring crisis proved copper can't be substituted. If this interested you, subscribe for more deep dives into materials making modern life possible. Thanks for watching. Can metal burn brighter than the sun? Sounds impossible, but one element does this every day, and we're about to touch its mystery right now. Imagine a material lighter than plastic, yet capable of withstanding loads that break steel. A material hidden in seawater, in stone, in the technology around us, but the way it's extracted looks more like alchemy than industry. And here's the thing. By the end of this video, you'll learn about a property of magnesium that even many engineers have never heard of. Ready to discover what giant furnaces, seawater, and 1,000-degree flames have been hiding? Magnesium is often called the metal that defies intuition. It's lighter than many types of plastic, weighing approximately 0.063 pounds per cubic inch, 1.5 times lighter than aluminum, and nearly 4 times lighter than steel. In your hands, it feels almost hollow inside, yet this metal demonstrates remarkable strength in alloys and can withstand loads its mass simply doesn't suggest. What's most striking is how it burns. Given sufficient temperature, magnesium produces light so intense that its brightness reaches close to 3,500 degrees Fahrenheit, and watching the flame without protection is impossible. That's precisely why magnesium flashes were once used in photography and pyrotechnics. During combustion, it forms white smoke of magnesium oxide, and the flame itself looks as if someone turned on a concentrated beam of sunlight. In nature, pure magnesium doesn't exist. It's bound up in minerals, and the 2 main sources are dolomite and seawater. Global estimates suggest that the oceans contain over 1.3 quadrillion tons of magnesium, making it one of the most abundant metals in a form accessible to humanity. However, extracting it from water is a complex and energy-intensive process. Picture an industrial facility on the coast where the sea is essentially raw material. Everything runs continuously through a system of powerful pumps. Pipelines stretch from the shore to the processing units, moving thousands of gallons per hour. The water flows into large open or enclosed basins resembling giant reservoirs, where it's filtered for the first time to remove debris, sand, and biological contaminants. After that, in similar tanks, a calcium hydroxide slurry is added. This happens through automated dispensers that feed the material into the water, so the reaction proceeds evenly. From the outside, it looks like a slow transformation of transparent seawater into a cloudy liquid, as if someone added fine white powder that gradually binds the dissolved magnesium into flakes of sediment. While the reaction continues, large mixers move through the pool, sometimes resembling windmill blades, only turned horizontally. They stir the liquid almost silently, so the sediment forms everywhere rather than clumping together in one spot. When the particles become heavier and start settling to the bottom, the liquid is pumped into the next settling tank. There it sits for several hours, and the solid fraction slowly settles, forming a dense layer that looks like wet cement. The upper part of the water is drained back into the sea or directed for retreatment, while the sediment is collected by special grabs or vacuum systems. Then the sediment is rinsed with fresh water and dried in powerful drying ovens that blow hot air at speeds capable of removing an entire layer of moisture in a minute. When the mass becomes brittle, it's moved to roasting furnaces. Inside, temperatures exceed 1,380 degrees Fahrenheit, and the material gradually transforms into magnesium oxide. From the outside, it looks like an endless white ribbon of powder, being fed by conveyor into the scorching chambers and emerging with a completely different structure. The final stage is electrolysis. The oxide enters sealed high-temperature chambers where it's mixed with salt flux. This happens either in smelting vats or in special crucibles, where the material gradually transforms into a thick, molten mass. The metal chamber walls glow red from the heat, and inside, the molten material looks like incredibly thick, scorching soup. At this point, electric current passes through it. You can only watch through protective windows, because everything inside appears to glow. Magnesium begins separating into tiny droplets that rise to the surface, since their density is lower than the molten mixture. It's collected using special ladles or drainage systems, and eventually the metal accumulates as shiny silver ingots, ready for further purification or casting into molds. In the case of dolomite, everything starts at the quarry, where the rock lies in massive layers. Extraction doesn't look like romantic stone chipping. It's the work of giant excavators, drilling machines, and blasting equipment. First, the rock gets crushed right on site. Massive jaw crushers chew through refrigerator-sized chunks and turn them into material that can move along conveyor belts. From there, the dolomite heads to factory hoppers, where machines precisely meter the flow and feed it into calcination kilns. The kilns work like giant tubes heated to 1,650 degrees. Inside, the dolomite slowly descends, while hot air, fed from below, passes through the entire layer of material. From the outside, you only see bright bands of glowing metal, but inside, something crucial happens. The dolomite breaks down into magnesium oxide and calcium oxide. After leaving the kiln, the hot mass travels along metal chutes and cools under powerful blasts of air. Next comes the stage where dolomite transforms into something resembling factory architecture. A tall tower with vessels, pipes, and tanks. Coke, or ferrosilicon, is fed into this tower, along with pre-crushed calcined dolomite. This mixing happens in specialized reactors that look like enormous drums, slowly rotating to ensure uniform contact between reagents. Everything appears as a continuous flow of dry, grayish powder sliding into the reduction furnace. Inside the furnace, the temperature climbs even higher, over 2,550 degrees. The heat inside is so intense that everything around glows with a dim red light. Under these conditions, magnesium oxide reacts with the reducing agent, and the metal transitions into vapor phase. This is one of the most distinctive features of magnesium production. The metal evaporates and rises through the furnace, while gaseous particles move into the condensation chamber. The chamber looks like a vertical steel cylinder, with cooled walls from the outside. Inside, magnesium vapors meet the cold surface, and the metal condenses as a shiny coating that resembles silvery frost. This coating gets periodically scraped off by mechanical scrapers or robotic manipulators operating in an environment with minimal oxygen access. The collected metal goes into protected containers, where it's melted again to remove residual impurities. The melting crucibles look like deep wells filled with glowing silvery molten metal, and extraction systems constantly work above them, protecting the metal from contact with air. The process ends with casting into molds, where magnesium cools and transforms into ingots. Each ingot represents the end of a long journey, from stone extracted by explosions to metal that emerged through evaporation and condensation. Global magnesium production holds steady at around 1 million tons per year. China supplies roughly 85% of that volume, while the United States, Israel, and Kazakhstan handle the rest. Interest in the metal grows annually because the aerospace, automotive, and electronics industries are hunting for the lightest materials possible. For example, using magnesium alloys in transportation cuts component weight by 20 to 35% compared to aluminum. That reduces fuel consumption and boosts overall efficiency. In electronics, magnesium shows up in laptop casings, camera bodies, and smartphones. It's not just light. It also absorbs vibrations well and dissipates heat effectively. In the United States, the share of magnesium in automotive parts has climbed from 3 pounds per vehicle 20 years ago to over 12 pounds in current models, and that figure keeps rising. Despite magnesium being lightweight, flammable, and extremely reactive, it's incredibly difficult to replace. It has a rare combination of mass, strength, and reactive properties that make it one of the most important structural metals of our time. And even though humanity has been producing it for only a century, the potential for its use hasn't come close to being exhausted. If current trends in aviation and electric vehicles continue, analysts predict global demand will reach 2 million tons within a decade. Ever wonder where trains go when they get too old for the tracks? This isn't like Grandpa's old car quietly rusting away behind the barn on the farm. A locomotive is a mountain of steel and copper weighing 450,000 pounds. Leave one of these bad boys sitting around, and it'll outlive your grandkids without even rusting properly. Today, we've come to a special facility where these steel giants take their final journey. This is a place where raw power meets surgical precision, and where everything that was once the pride of the railroad gets transformed into cold, hard cash and raw materials for new skyscrapers. We're going to watch how they dismantle monsters that spent decades hauling thousands of tons of freight across the entire country. It all starts with what we call environmental cleanup. A locomotive isn't just an iron box. It's basically a chemical warehouse on wheels, and none of that stuff is good for grass and trees. Before the guys with giant shears get to work, every fluid gets drained from the machine. Just picture these numbers. One large passenger or freight train can hold up to 5,000 gallons of diesel fuel. On top of that, there's another 400 gallons of engine oil and 300 gallons of coolant. That's a whole lake of chemicals that needs to be pumped out very carefully. Workers use special pumps that suck out every last drop, because even a single oil stain could trash the entire facility's reputation with environmental agencies. It's long, messy work, but without it, nobody's allowed to cut metal. But the really interesting stuff is hiding behind the walls. Inside a single locomotive, there's about 5 miles of copper wire. Copper is a recycler's treasure because its market price is astronomical compared to steel. Workers strip away the casing and pull out entire bundles of cables weighing thousands of pounds. It's tough manual labor because machines haven't yet learned to snake wires out of the tight channels of the fuselage quite so cleverly. And now, hold on tight, because we're moving to the heart of our iron beast. The locomotive engine, a 16-cylinder giant the size of a small minivan. One of these engines weighs about 35,000 pounds. To get it out, you have to remove the entire roof of the locomotive. A giant crane lowers its claws, hooks this block, and slowly lifts it into the air. It looks stunning, because you're watching something that produced 4,000 horsepower just hanging above the ground. If this engine can still be saved, it'll be sent for a major overhaul and serve another 20 years somewhere on a ship, or as a backup generator for a hospital. But more often than not, it goes to scrap too. They dismantle it into parts, aluminum pistons separate, steel block separate, cast iron components separate. Nothing here gets thrown away just like that.